dam owner workshop on the need to know basics of owning a dam. For those of you that don't know me, my name is Karen Goff with the Department of Water Resources. I manage the state's dam safety program, and I just want to welcome you, and it's great to see everybody here. Thanks for joining us this morning. A little background on this workshop. So we're hosting this in conjunction with the Association of State Dam Safety Officials, or ASDSO. And so one of the great things that that organization does is provide education and resources for dam owners. So they've developed this workshop for states to use in their states. And so they've provided the content and the instructor. And so our instructor this morning is Eric Ditchy, and he's an expert in the field of dam safety. And he's done a lot of these workshops through ASDSO for other states. So he's a great resource for us to have today. And the other thing I just wanted to mention is that this workshop's being funded by a grant that we get at the DWR through FEMA, through the National Dam Safety Program. So I just want to put a plug in for that. Allows us to do things like this. So with that, just want to hand it off to Eric so he can get started. So welcome, Eric, and thank you for being here and doing this for us. And it's all yours.
Okay, thank you, Karen. It's nice to be in North Dakota, even if it's virtually. I was actually in South Dakota doing a similar owners workshop back in March, and it's a beautiful part of the country. I'm going to turn my video off as I'm presenting, just so that we don't use up bandwidth. So good morning, everyone. This is the introductory dam owners course, need to know basics of owning a dam. This is my contact information. Certainly, you're welcome to reach out to me after the course if you come across something that raises a question relative to what we presented today. So there's an email contact and also conventional mail contact. I've been doing this for nearly 40 years. I live in New Jersey. Most of my experience is in the East Coast of the United States. Been lucky enough to spend most of the 40 years of my career working on dams, both inspections and evaluations of existing dams and design of new dams. As we said a little bit earlier, Karen's going to help with the presentation. The second session today, she will cover the rules and regulations for North Dakota. This is her contact information, and I'm sure that if you guys, if anyone has any questions relative to either what's presented today or relative to their dam, certainly Karen would be more than happy to assist you with any of those things as well. We've got a number of goals that we're hoping to achieve today. And the focus of this entire workshop is towards owners of dams. So it's not terribly technical, although we do touch upon some engineering aspects, hopefully to get dam owners to sort of understand the way dams work and perform. So some of the goals we're looking to achieve today are to give you a better understanding of the dam safety laws and regulations in North Dakota, understanding of operation, maintenance, and inspection of dams, issues of public safety, dam owner liability and security at your dam, various dam failure modes, developing and implementing emergency action plans, and then finally, some repair projects. We'll talk about types of repairs, some potential costs for those repairs, what available funding there may be out there to help pay for some of those repairs, and then also some guidance in hiring an engineering consultant. The agenda for today, we do have quite a bit of information to get through, so it should probably, unfortunately, run most of the day. We're going to start with session 1, which is an introduction. Session 2 is going to cover North Dakota's dam safety laws and regulations. Karen will be presenting that around mid-morning. We're hoping around roughly 10:15 we'll break for about 15 minutes, then get back together, say around 10:30 for session 3, which is dam failure modes and case histories. It's a fairly extensive session, so that'll probably take the second half of the morning. Then we're looking to break for lunch around noon. Since this is a virtual workshop, we're only given about 45 minutes for lunch. We're hoping that'll be enough for everyone to get their lunch and eat. Certainly, because it is virtual, you're welcome to eat while I'm presenting, so that's not a problem. So we're going to get back from lunch around 12:45, then cover session 4 and 5. We'll have a mid-afternoon break, roughly around 2:30, and then finish up with sections 6 and 7. There is some wrap-up information at the end, course evaluations, some things like that. And I think Jennifer will probably get back on the webinar to discuss those things at the end. We've mentioned the Association of State Dam Safety Officials. They're the ones that basically put together the content of this course, as well as several others. It is the leading national nonprofit association dedicated to dam and levee safety in the United States. It was created back in the early 80s in response to an urgent need for establishing and strengthening dam safety programs across the country, and also to improve communication between the various state dam safety programs. And it has grown to the point now where it is the premier professional organization committed to ensuring the safety of dams in the United States, which is really quite a large responsibility. The things that ASDSO does to improve dam safety, it's quite a bit. They first and foremost support the state dam safety programs, and they provide that support in a number of ways. They develop a cohesive and engaged community committed to the ASDSO mission. They educate dam owners and operators, and one of the ways they do that is this course we're doing today. They increase public awareness of the role of dams in society, the risks that they present, and the importance of dam safety and preparedness. They also advocate for laws, policies, government programs that serve to improve the safety of dams and reduce the risk to the public. They strengthen and support a coordinated effort to improve the safety of levees. Following Hurricane Katrina and the devastation it wreaked in Louisiana with the levees down there, the levee safety program sort of blossomed and is sort of following a similar track to what the dam safety program is across the United States. So that's a relatively new addition to one of the responsibilities ASDSO has taken on. They also advance and expand the technical expertise of dam and levee safety practitioners, and they promote innovative approaches to funding dam rehabilitation at the state and federal level. ASDSO membership. I'm hoping that some of the dam owners in the audience are members of ASDSO. If not, I would strongly encourage you to become a member. Over the next couple slides, we're going to touch upon some of the information that ASDSO makes available to dam owners, which is all really quite useful. So becoming a member of ASDSO is a way to join with others to work towards safe design, operation, and maintenance and upkeep of all dams, whether they're privately or publicly owned. And over the years, ASDSO has grown itself and benefited from the involvement of many types of members. So in the membership, there are dam owners like yourselves, owners of small, medium, and large dams. There are regulators such as Karen, engineering consultants like myself, contractors that specialize in dam repairs and rehabilitation, various manufacturers and vendors of products that are used at dams. So it's quite a cross section of people that are involved with dam safety and dam ownership. So again, it's a great organization. I forgot to say kind of at the beginning, as I was going through the agenda today, we do have quite a bit of information to cover. Although an interactive presentation is oftentimes nice, it's difficult to often do that when we're presenting virtually like this. So I would ask that if you do have questions, I may stop periodically through some of these sessions and ask for questions, or I will stop at the end of each session and ask for questions. So rather than jumping in during the session, if you could hold whatever questions you have to the points that I ask for them, generally at the end of the session. You could also welcome to type in questions in the chat box, which I do have on my computer, but I'll only kind of keep an eye on it part of the time. So if there's some questions in there, I'll try to address them at the end of each session as well. The webpage for ASDSO is right here. There's a section devoted just for dam owners. And actually at the bottom left of each of these slides is the website as well. But once you get into the main website, like I said, there is a tab called Resource Center. When you click on that, then you'll see resources for dam owners and operators. And that information obviously is there and developed specifically for owners and operators. This is some of the information that is contained on the website. There's information about being a responsible dam owner. There's a Dam Owner Academy, Dam Owner Education video series is contained there. I'll go into a little bit more detail on all of these. There's also a listing of workshops. Again, ASDSO supports and conducts these workshops across the country. They also put on technical seminars. There's a variety of educational means that they put on, around the country. So this workshop is just one of these types of things. There's also a series of fact sheets that contain some great information, as well as some general guidance for dam owners. It's also an area where you can meet knowledgeable dam owners and regulators and obviously interact and discuss similar problems. And there's also a listing of external resources for dam owners. Now, in particular, the Dam Owner Academy, it's an owner education video series. There's a total of 8 of these videos they have there now. The bottom 4, which I've highlighted in red, are brand new. They were just added to the series this year, 2022. So we now have a total of 8 of these. The videos are only about, say, 8 to 12 minutes, maybe 15 minutes long each. Again, not terribly technical. They're intended for owners of dams, people that aren't necessarily engineers or have engineering background. And a lot of what we're covering today is very succinctly covered in these 8 videos. Eventually, they may be putting me out of business here, but they're very well done and quite easy to watch and listen. So I encourage you to go online to look at them. There's also, educational webinars. There's a section for on-demand webinars that ASDSO has. They've got a total of about, I think it's 125 or 126 webinars available. Some of them, or quite a few of them, are intended for dam owners, as well as there's more technical ones that are intended for engineering professionals. There is a webinar on the titled Introduction to Inspecting Dams for Owners and Operators as part of that list of on-demand webinars, and that is free to dam owners as part of this education program. And again, it gives you there's a portal on the website to get to the list of all these webinars. Some of them do cost some money, but there are a number that are free. And like I said, the ones, there's quite a few that have been developed for dam owners, so they're not overly technical. There's also a list of these fact sheets. There are 23 fact sheets right now. They're only 1, 2, maybe 3 pages long, but generally only 1 or 2 pages. And they cover a variety of topics that are of interest to dam owners. The list of them is on the left of this slide. You can kind of go through that and see, excuse me, the types of topics that are covered here. And there's one highlighted there, kind of blown up on the right, on internal erosion of earth dams. So, sometimes they do cover more technical topics such as internal erosion of earth dams, but they do it in a very basic way. So it's quite easy to read and understand. So again, another great source of information. ASDSO has a standing committee titled Dam Owner Education Committee, and they oversee a lot of these different educational programs, including these workshops like the one I'm doing today. They have 3 of these workshops put together. The first is the one that we are presenting today, the Need to Know Basics of Owning a Dam. Then there's a Dam Engineering 101 workshop, which goes into more of the engineering that goes into evaluating and designing a dam. And then finally, the third is dam maintenance and operation. Each of these is a full day workshop and can be presented either in person or virtually. Certainly the best local dam safety resource is Karen and her department and her website, where they have all the information about the state dam safety regs, which she'll be discussing in a few minutes in session 2. Some additional dam safety resources are the NRCS, Natural Resource Conservation Service, which is the old SCS, Soil Conservation Service. Also, the U.S. Department of Agriculture, the local soil and water conservation districts have good information typically about dam safety. Then more on a federal level, the U.S. Bureau of Reclamation, Corps of Engineers, Federal Energy Regulatory Commission, all at a federal level own dams or responsible for dams, and they have a lot of information on their websites. And then back locally, there's certainly consulting firms locally, regionally, that can provide resources for dam safety. Okay, an introduction to dams. So I'm just kind of reading through the chat to make sure I'm not missing anything. Jennifer did make a comment relative to those videos that I highlighted, that there are currently 8, but they do have plans for adding additional videos in the future. So, there will be more and more information that ASDSO puts together and provides for dam owners. So that's good information. As far as introduction, excuse me, to dams, we're going to cover today various parts of a dam, different dam types of spillways. There's many different types of spillways, functions of dams, and then some general terminology. So hopefully, as I present this information, it's what I'm saying is clear to everyone. You understand, the various terms that are being used. This is a graphic of an earth embankment dam, starting from the labels sort of from left to right. Of course, the top of the dam is referred to as the crest. The slope that is adjacent to in contact with the reservoir is referred to as the upstream slope. The slope on the opposite side of the dam is the downstream slope. In this particular depiction, there's a principal spillway, which is a concrete structure out in the reservoir. It's drawn as a drop inlet riser or a riser structure. Water would flow into the riser. It's opened top. The top of it is open. So the water flows down into the top of the riser, drops down vertically, and then would flow horizontally under the base of the dam through some type of outlet pipe or outlet conduit. All spillways have basically three components: a control section, which is the section that the water flows over. That control section establishes the normal pool level, also the efficiency at which water can pass into or through the spillway. Then there's a conveyance structure where water then is conducted from that control structure to the downstream tow. Here, the conveyance structure is that horizontal conduit or pipe. And then at the outlet structure, because the water has gained energy, velocity and energy flowing from the reservoir down to the downstream tow, typically there's some form of energy dissipation at the downstream tow. Here it's labeled as the outlet works. I'm not sure if you folks can see my mouse, but I'm highlighting the outlet works. Many earth dams, in fact, all dams will seep or leak a little bit. In and of itself, seepage or leakage is not necessarily a problem. It's generally good practice to design into a dam some kind of drain system. Certainly in earthen dams, earth embankment dams, or rock fill dams. So here we're showing a tow drain running along the downstream tow and then outletting into that concrete outlet works as well. The area where the dam meets the natural ground or the abutment is the abutment contact or the groin. On the right side of this slide is either is called a second, it's another spillway, can be referred to as either emergency spillway, secondary spillway, auxiliary spillway. All of those basically mean the same thing. In this type of layout, the principal spillway, that drop inlet riser, is sized to pass only up to a certain size storm event. And then above that storm event, water would then flow through this emergency or auxiliary spillway. A convention we have in dam engineering is referring left and right. If you're standing on the crest of the dam, looking in the downstream direction. So the reservoir would be to your back, and we refer to elements that are left or right of that. So the emergency or that auxiliary spillway would be located on the left abutment of this dam. This is a cross section through a typical earth embankment. There's a number of elements here that are worth pointing out. Again, the top of the dam is referred to as the crest. In the center part of the dam, the material that's making up the dam, we're showing a central core. You see the trapezoidal shape there, right in the center of the dam is the core. An earth dam that has a core, and then the material outside the core would be referred to as the shell material. That type of dam is called a zoned earth embankment, meaning that it's made up of various zones of material, different material. The core material would be a fine-grained, low permeability material such as silt or clay. That would be the zone of material that provides the primary barrier to water seeping through the dam. When you have a central core like that, then you would typically have coarser grained sands and gravels that are used to construct the shell of the embankment, which is the materials on either side of the core. As I mentioned before, it's good practice to put a drain system in an embankment dam. So again, typical design when you have a zoned embankment like this with a central core would be to construct a filter drain system on the downstream side of the core to pick up whatever seepage comes through the core. So what's being illustrated here is a near vertical filter, oftentimes referred to as a chimney filter, chimney drain, that then connects to a horizontal element, which is referred to as a blanket drain. So any seepage that's coming through the dam, through the core, then gets picked up in this drain system and safely conducted out to the downstream toe. At the downstream toe, you can see where the blanket drain then is connected to this toe drain, with that also then continues to collect the seepage and direct the seepage to a point at the downstream toe. It's good practice, again, to collect the seepage into a pipe like that can be discharged at a given point, so that the amount of seepage coming through the dam can be monitored. If you don't have any type of internal drain system, then the seepage is free to flow out at any point along the downstream slope or toe, and it will be very hard to monitor the amount of seepage. And by monitoring it, you can then see if there's changes in seepage quantity that might indicate some type of developing problem. I'm going to ask a question if someone can just answer, but can you see my mouse moving on the slide?
I can't, Derek.
Okay.
Cannot.
How about now?
Now I can.
Now you can. Okay. I was on the wrong monitor. Okay. It will help me illustrate some of the elements that I'm referring to. Thank you, Karen. So talked about this core, central core in a zoned embankment, this drain system. Seepage is coming through the dam. What it will do is saturate the soil materials so that the voids between the individual soil particles are full of water. There's a point where the saturated soil, the areas that the voids are completely full of water, stop. And then above that, there's areas of soil that the voids are just maybe moist or dry. That contact between the moist or wet soil and the dry soil is called the phreatic surface. Above the phreatic surface, the soils are just moist or dry. Below it, they're fully saturated, meaning the voids are full of water. This concept of this phreatic surface we're going to mention or refer to a couple times today. It's very important in both design of a dam and an evaluation of existing dams. The phreatic surface is closely connected to the amount of seepage that comes through the dam, where the seepage exits at the downstream slope, which is very important, and where that seepage exits then also affects the overall stability of that downstream slope. In general, you want to collect the seepage like we're trying to do here with this vertical filter and blanket drain, so that the phreatic surface is intercepted and then all the seepage runs through the drain, so that ideally all of the soil above this drain system should be dry. If for some reason this drain system is clogged or not designed properly, so it's not collecting the water, the seepage water like it should be, then the seepage is going to extend up. The phreatic surface is going to extend up above this blanket drain into the downstream slope. And the way it's shown here, this line looks like it's exiting the downstream slope about a quarter or the third of the way up the height of the dam. That is a bad situation. The higher that the phreatic surface exits the downstream slope, that means the majority of that downstream slope material is saturated. Means that the soil there is weaker than if it is dry, than if it were dry. If the drain system were working, and potential failure modes that we're going to be talking about later on today. So just keep in mind that that concept of the phreatic surface. We're also illustrating the same principal spillway structure that we showed in that previous graphic, where we have a concrete riser structure out in the reservoir. That is the primary spillway. So the top of that riser structure sets what the normal pool elevation is. Water flows over the walls of the riser structure, drops vertically down, and then flows horizontally through the base of the dam through either a pipe or some type of conduit outlet. Again, the water has gained energy and velocity by dropping down and coming through this pipe. So there is some type of energy dissipation, energy dissipating structure at the outlet end of that outlet pipe. Here it's referred to as a stilling basin. I'll show a couple examples of these types of structures as we go through this section. One of the, again, possible failure modes, and we'll show some examples of this, are penetrations through an earth embankment. Anything that penetrates through the earth embankment, such as this outlet pipe. It is difficult when you construct these new to get the soil adequately compacted around the outlet pipe, and definitely the bottom half of the outlet pipe. It's very difficult to get soil compacted under the bottom half. So it is common. It is a preferential seepage path for seepage to follow the outside of these pipe conduits. And the concern is that if seepage is allowed to flow along the outside, and if it gains enough velocity, it can start to pull fine-grained materials, fine-grained soil materials from either the embankment or the foundation. And that starts to erode internally the embankment or foundation material. And we're going to show some examples of that as well. So what oftentimes is constructed around these pipe penetrations is this anti-seepage filter. It is basically the same type of material that you would use to construct either the vertical filter drain or perhaps the blanket drain, but most likely the filter drain would be sort of a clean sand that would be constructed around any penetration like that pipe conduit. As I said, hopefully that won't happen again. Did you hear the discussion about this anti-seepage filter? Was I still?
We heard that part.
You heard that part? Okay, so then I think the next thing I went into is freeboard, this concept of freeboard, which will play an important part in some of the discussion later on different methods or modes of failure. It's basically a dimension between the crest of the dam and it can be either measured down to normal pool, which is the normal operating pool level, or more importantly, maximum pool, which would be the level of the pool that rises during whatever design storm the dam is supposed to be able to safely pass. In general, from that maximum pool surface elevation to the crest, you want a minimum of about 1 foot of freeboard. Again, in other words, the maximum pool level should be at least 1 foot below the low point of the crest. And on big reservoirs where you get potential wave action and run up from waves, you could also perhaps increase that freeboard to 2 or 3 feet. So we will revisit that concept of freeboard later on today. It's a pretty simple detail or section, but there's a lot of important concepts here, so I had to spend some time there. All right. Some of the common terminology, which we've hopefully illustrated most of it already, are the upstream and downstream slopes, the abutments, and again, oriented left and right. If you're standing on the crest looking downstream, left and right, the area where the dam meets the natural abutments is the groin. Various spillways, we're going to show some examples of those, outlet works, internal drains, again, why they're so important. They intercept that phreatic line and safely conduct seepage to the downstream toe. So as we continue through here, we're going to show a couple different failure mechanisms, and internal drains and phreatic surface play a big part in that. Riprap, I don't think we've covered yet. I'll show some illustrations of that. It's basically large rock that's quite angular. Generally, it's shot, from bedrock, so it's quite angular. It's used typically wherever you need to prevent erosion. So commonly put on the upstream slope of the dam to prevent erosion of the upstream slope due to wave action. Also in some of the outlet areas where, again, the water's coming out of the spillway at high velocity. And also show, again, examples of that. Freeboard we just talked about. Instrumentation, not all dams are instrumented, but many of them are. There's different forms or types of instruments, and they each measure different things. Survey monuments are sometimes put on dams. They're intended to monitor any potential, generally vertical movement, any settlement of the dam. Piezometers are wells essentially installed vertically into an embankment dam and into the foundation. And the piezometers are intended to measure that phreatic surface, where the phreatic surface is, and if there's any pressures due to that either seepage or water that's in those pores of the dam and foundation. And then seepage weirs are oftentimes installed at on the pipes that collect the drain, the internal seepage drains, and seepage weirs then allow measurement of the quantity of seepage. Again, looking for any changes in that over time. So here's some examples of these different terms. This is obviously a very well maintained earth embankment. You can see the photos looking right down the crest of the dam. You can see the upstream and downstream slopes. The upstream slope is to the right, downstream slope is to the left. You can see the reservoir, and again, a concrete riser structure in that reservoir. Here is a photograph of the abutment contact where the embankment on the left side of the photograph is coming in contact with natural ground on the right. So that is the abutment contact, or the groin. That area oftentimes is subject to erosion due to just surface runoff. You can get, just during a normal rainstorm, you can get water flowing down the downstream slope and also flowing down off the abutment, and it will tend to concentrate there in the contact area or the groin. So that area is subject to erosion just due to surface runoff. So you can see that there's been riprap, or that coarse rock, placed up along that contact area to form sort of a gutter. Here's an example of an overflow spillway on an earth embankment dam. It's a concrete overflow spillway. I mentioned that all spillways have generally three components. So the control section here is this weir structure, basically at the reservoir level. So again, this sets normal pool elevation. Also, it's sized to pass a certain amount of storm flow over. This is the conveyance structure, which is a concrete chute, and conveys water to the downstream toe. This would be the energy dissipation part of the spillway. It looks like it's a plunge pool, meaning that there's water that sits down in here, so that as water comes over the spillway, it accelerates down this chute or this conveyance channel, and then it impinges upon this ponded water here, slows down, loses most of its energy before it's discharged into the natural stream channel downstream. This is a riprap stilling basin. This is the energy dissipating element of the spillway. So the spillway is some type of structure, riser structure or inlet structure in the reservoir. It's connected to a pipe that runs through the base of the dam. You can see the pipe exiting there. The water drops then into an excavated basin that's lined with riprap. And again, the concept's similar to the previous photograph, that water will sit in that stilling basin, so then any discharge coming out of the pipe just flows into the ponded water, loses its energy, and then can flow downstream. You can see the natural stream channel to the right of the photograph. No erosion or instability of that channel, so it implies that that stilling basin is working as it's intended to. Trash racks are an element put on the upstream end of the spillway in the reservoir, intended to stop any type of debris from flowing into a closed spillway, such as a riser structure and outlet pipe. So the design of the trash rack is actually quite critical. You want the openings of the trash rack to be big enough that small debris will pass through the spillway system without becoming clogged, but the spacing fine enough to capture larger pieces of debris that, if they did get into the spillway, could get stuck and clog the spillway. I mentioned riprap, which is that shot angular rock used in areas of dams that are subject to erosion. Here it's placed along the upstream slope to prevent any erosion of the upstream slope due to wave action or fluctuating pool levels. Example of a masonry gravity dam, as I understand it from Karen, that North Dakota basically has just all earth embankments. So although there's some elements in the presentation depicting gravity dams, we're not going to spend much time on them. So we'll continue on. Freeboard, already spent some time on that cross-section graphic, but here is an actual photograph illustrating, again, the dimension between the pool level and the crest of the dam. And one of the more critical freeboard dimensions is that dimension between the low point and the crest and the maximum water surface in the reservoir during whatever the design storm is. Here's some examples of the instrumentation I spoke about. The monitoring well, again, is a vertical well, generally installed either in an embankment dam or down into the foundation of the dam. It's basically used to measure level of that phreatic surface or any pressure of the water in lower levels of the embankment or foundation. The bottom photograph is the seepage monitoring weir, where the tow drain pipe would come into this box, and then water would flow through that V-notch wall. And then you can measure the depth of the water, and there's formulas to give you a calculation of quantity of water. And the idea of instrumentation is that it's monitored on some regular basis, with the idea of that it would identify any type of potential negative trends in the dam, either the amount of seepage increasing, pressures of seepage or water in the dam increasing, things like that that can be indications of some serious problems. Okay, various types of dams. The most common type of dam is either an earth or rock-filled dam. collectively called an embankment dam. If it's composed of earth materials, silts, clays, sands, gravels, it would be an earth embankment dam. If it's composed of larger, coarser grained, like riprap, rock materials, it would be referred to as a rock-fill dam. Corps of Engineers has an inventory of dams across the United States, and about 90% of the dams fall into that category of embankment dam. The remaining types are various forms of either concrete or masonry dams that can either form gravity section, arch section, or buttress section. But again, we're going to focus today mostly on the embankment dams. There are even some less frequently used types. There are some steel dams. Inflatable rubber dam is really a type of gate that's used on spillways to raise or lower the water level. And I'll show an example of that. And historically, there are wood or timber dams that were quite common back. Construction of these was common back in the late 18 or early 1900s. And you still find some of them around today. Certainly here on the East Coast, we do run into them. This is a nice graphic that illustrates what typical cross section would be for these different types of dams: embankment, gravity, arch, and buttress. Like I said, the vast majority of dams are embankment dams, and the reason is because the way these are constructed, whether it is an earth embankment or even a rock fill embankment, you have these sloped, the upstream and downstream slopes. It forms a relatively wide base width. It has to have a certain base width to be stable. Because it is so wide a base width compared to the other types of dams, you can see that it's much wider than a gravity dam or say an arch dam or even buttress dam. It allows these dams to be constructed on a much wider range of foundations. You can put an embankment dam on a soil foundation, on a rock foundation, pretty much any type of foundation, whereas the concrete dams, the gravity, the arch, the buttress, because concrete is a rigid and brittle structure or material, it requires a relatively stringent foundation, something that's quite solid, not subject to any type of settlement or differential settlement. So most concrete dams are constructed only on rock foundations. So because of the limitations in the types of foundations the concrete dams could be constructed on, there are far fewer of them than embankment dams. Again, some examples. Here's an embankment, earth embankment dam viewed from the downstream side. That's the downstream slope. Here is a rock fill embankment. You can see the coarser grain material on the downstream slope. This is a concrete gravity dam constructed using roller compacted concrete, which is a relatively new construction technique, first applied to dam construction back in the 80s. It's basically a low cement, low water content concrete that's placed using earth moving equipment. So it's placed like earth fill in horizontal lifts. Because of that and the low cement content, it doesn't generate as much heat as conventional cast in place concrete. So roller compacted concrete can be placed at much greater placement rates than conventional concrete. So it ends up being much cheaper than conventional cast in place concrete. So really since the 80s, any new concrete gravity dam generally has been constructed using this roller compacted concrete method. Concrete arch dam, which most people are familiar with the look of that. These require a very specific type of foundation. The valley has to be relatively steep on both sides. because for the concrete arch to work, you can see obviously that it's forms an arch into the upstream direction. So the loads applied to the dam from the reservoir are transferred through arch action to both the foundation and the two abutments. So the bottom foundation and two abutments have to be relatively competent rock, and the geometry of the valley has to be such that it's relatively steep for a concrete arch dam to work properly. And concrete buttress dam, similar to gravity dam, except that there's either vertical or inclined concrete slab on the upstream side, and the loads then are transferred to those vertical buttresses that then transfer the load down to the rock foundation. Example of a steel dam. I've never seen one of these in person, so they are not very common at all. This is an example of the rubber dam. Essentially, it's a inflatable bladder. You'll see these oftentimes used to retrofit an existing dam, put on the crest of a dam if for whatever reason they want to be able to either raise or lower the crest, let's say for hydropower generation or even water supply. You can inflate the bladders so that the bladder basically fills up, which will raise the water level behind it. If you need to lower that water level, let's say in advance of a storm, then the air pressure can be relieved and the bladder deflated, and it collapses, and that results in lowering the reservoir. Here's an example of a timber crib dam. Again, you don't see this very often in new construction, but certainly they were commonly used back in the beginning of the 19th century, beginning of the 20th century, 1900s. So there are plenty of them still out there. Here's going to be some examples of various spillway types. Conduit spillway, open channel spillway, and weir spillways. I'll show you examples of each of these. Within the conduit spillway category, there's a riser and conduit, box drop and conduit, morning glory riser and conduit, and slanting conduit. So these are all spillways where there's some type of structure out in the reservoir that water flows into. Most of them are vertical structures, so the water would flow down vertically and then horizontally out through some type of pipe or conduit. So here is a spillway riser inlet out in the reservoir. The rack on top is a trash rack. That plate is an anti-vortex plate. This type of spillway, as the water flow increases and the depth of water reservoir level increases, so the depth of water into the spillway increases, it's common that you start to get a whirlpool or vortex, which basically introduces and pulls air into the spillway system, which reduces the capacity, reduces the flow rate through this. So that plate installed the way it is prevents that vortex from forming. So it actually improves the hydraulic efficiency of this type of relatively small diameter pipe riser. This is a close-up example of some of those that you saw in those graphics earlier, where it's a drop inlet, it's a concrete structure. The Soil Conservation Service, SCS, which is now NRCS, standardized the design of these. You can see that this is actually constructed within the upstream slope of the dam. That does a number of things, provides several benefits. One, because it's supported by the surrounding soil, the reinforcing and the thickness of the concrete can be minimized versus if this were freestanding out in the reservoir itself. They also did a lot with the different trash racks. Here you can see these heavy horizontal bars and then a finer grain screen up here. The actual spillway crest for this is down in the lower part of this this rack system, and you can see the way these heavy bars are oriented. the idea is that as water, if there's debris floating down, water flows into this, the debris builds up against these racks. And then as the reservoir level starts to drop, because these racks are inversely inclined the way they are, the debris should just fall off of them and collect around the sides of the tower. Because the tower is embedded in the slope, it's quite easy to get to the tower once the water recedes a little bit, and then whatever timber debris or whatever the debris is can be pulled up on the slope and pulled away from the inlet tower so that it doesn't clog up during future storm events. And then those horizontal bars are designed to pick up the larger say pieces of debris, and then this is a smaller rack system above it that would prevent smaller stuff from flowing into the tower. There are several gates on this tower as well, and you can see each of those are equipped with trash racks as well. Morning Glory spillway, it's similar to the first slide. Basically, it's a vertical concrete structure, but larger diameter typically. And here you can see it's equipped with a trash rack as well to prevent debris from flowing down into that Morning Glory. Here, the previous three spillway structures are vertical, so the water drops down vertically and then flows horizontally through some type of outlet pipe. Here is a hooded inlet pipe, so this is actually constructed through the embankment on an incline, so that the upstream end is obviously here at reservoir level, and it is as it goes through the reservoir, it's on an incline so that it discharges, at the downstream toe. There is a hood on it that's this triangular piece here. Same type of idea as far as that anti-vortex device. As the depth of water increases over the top of this pipe, again, it would oftentimes form a whirlpool, and this plate prevents that from happening, which improves the efficiency of the pipe. Those were conduit spillways, so essentially the water flowed through closed conduits or channels from the reservoir to the downstream toe. Alternatively, there's open channel spillways. They can be either earth lined or vegetated in some way, concrete lined, or excavated in rock, so that's a rock cut spillway. Here's an example of an earth dam. The auxiliary spillway is in the foreground, and it is grass lined, as you can see. This is an example of a concrete chute spillway. So the conveyance structure here is lined with concrete. An example of that chute or conveyance structure being actually in rock cut. The control section, which is the upstream most element of the spillway, is what controls the reservoir level, as well as the amount of flow that comes through the spillway, typically designed to pass up to a certain design storm. Again, there's various types. There's a drop inlet, broad crested weir, labyrinth weir, sharp crested weir, and a gated spillway. Just some examples. This is a drop box inlet. You can see it's three-sided box. This particular one has a notch right here in the upstreammost wall of the spillway, so low flows can flow through this notch. As storm flow increases, the reservoir rises up. It can then flow over all three sides of this box. So that's a drop box spillway. This is an OG crest spillway. It just happens to be curved in plan, but it's not really meant structurally to be an arch. But the shape of that OG is quite important because of its curved shape. It's actually the most efficient weir shape that there is. So when you're designing the spillway to pass a certain amount of flow, if you design it to be an OG crested weir, you can pass the greatest amount of flow in the smallest footprint here, because it gets its most efficient cross section for spillway crests. Another type of weir is a labyrinth weir, which is essentially a sharp crested type of weir that is articulated or zigzag, if you will, in plan, so that you get quite a bit of weir length compressed into a small footprint for the overall spillway. So the efficiency here is that you don't need as much foundation concrete or foundation support, because again, this is compressed into a relatively small footprint. The outlet chute again is much narrower than if this spillway crest was stretched out linearly. So it tends to be a relatively cost-effective spillway configuration. You get a lot of spillway capacity within a relatively small footprint. Broad crested weir, just well, back to the labyrinth, I refer to this as a sharp crested weir, articulated in plan. So the dimension of the weir itself, it's basically just a vertical concrete wall. It might be 9 or 12 inches wide across the top. That type of dimension would result in basically being a sharp crested weir. Here you can see how flat and wide the top of this spillway is. This is probably 12 or 15 feet wide. So water basically just flows over the top of this and then down this concrete chute, the conveyance channel, into this stilling basin at the downstream toe. So this is referred to as a broad crested weir because of its dimensions. This would be the close-up of another sharp crested weir, curved in plan. And a gated spillway, I think is pretty self-explanatory. Variety of different types of gates that you can put on top of the spillway crest. The idea for all of them is the same, that when the gate is in its working position, if you will, it basically raises the crest of the spillway so you can impound more water. If water is valuable for the purpose of the dam, such as hydroelectric, water supply, even navigation, you oftentimes see gated spillways. And if for whatever reason they have to lower the reservoir level, oftentimes they will do that in advance of an oncoming storm. They can raise the gate out of the way, release whatever water stored behind it, and essentially reduce the spillway crest, but by whatever dimension or height the gate is. Here are steel gates that rubber dam, the inflatable bladder, could be used here as well. Same type of concept, other than it's really not a mechanical gate. It's just the bladder that gets filled with pressurized air. So regardless of the type of dam, all dams must be properly operated, maintained, and inspected by the owners. The various functions of dams. Dams can be used for flood control, water supply, power supply, waste impoundment, wastewater impoundment, irrigation, navigation, or recreation. And many times they're mixed use. You get multiple purposes going on. This is an example of a flood control dam and reservoir. Many times there is no permanent pool at all. The flood control structures are dry, and then when there is a storm event, water will fill up behind it, but then is allowed to flow out. In this particular example, it looks like there is a permanent pool at a lower elevation. You can see on the left-hand side of the photograph, there's a wide auxiliary or secondary spillway that will then be able to pass certain flood flows. Because of that, there's quite a large amount of freeboard between that normal operating level and the crest of the dam. So this dam is able to store quite a large flood discharge and then let it out through that auxiliary primary spillway over time. An example of just a water supply dam, obviously it's surface storage for water providers. So many times there's a water treatment plant either adjacent to the reservoir, or if not, the water is either piped to the water treatment plant or is discharged into a channel that then flows to a water treatment plant where the water is withdrawn. Hydroelectric power, generally kind of obvious due to the power station at the toe. You'll usually see, the high voltage lines coming in and out of the facility. Waste impoundment in the mining industry, where they use water to extract different types of materials from the mines. Then the water gets sent into these lagoons for the waste material to settle out. And then the water is reused again in the mine. These can be sometimes dangerous because they often are built with very little engineering, and depending on the level of regulation in the state, sometimes they're not even that well regulated. Wastewater treatment plants oftentimes need lagoons for the water to settle. Same concept as sort of a tailings dam, just a little smaller scale. But oftentimes these settling basins are constructed, by dams or impounded by dams. So, they're used in the waste treatment industry, can be used for irrigation in agricultural areas. Dams can be used to help navigation on rivers. So by building a dam, you increase the depth of water upstream the dam, which allows navigation to extend further up that particular river course. Of course, if you put a dam across a river that's used for navigation, then you have to have adjoining lock system that would allow the ships to pass the dam and obviously change elevation from the water surface on one side of the dam to the other. And then the most commonly use for reservoirs is recreation. That's actually by quite a bit. That's the most common type of dam and reservoir use. That is the end of session 1. Do we have any questions with anything that I covered there? Nothing? Am I still online? Does everyone hear me?
Yes, we hear you. I think they're just shy.
That's a scary thought. I just finished talking and maybe I wasn't there. Okay, I don't see anything in the the chat box either. All right, I'm going to turn the operation over to Karen then, and she can present session 2, which is North Dakota Dam Safety Rules and Regulations.
Okay, thanks, Eric. Is everybody seeing my slides?
Yes.
Okay, perfect. So this is a fairly short presentation. It's intended to just be kind of an overview of kind of the big stuff related to laws and regulations regarding dams. And I guess to start with, so our dam safety program is part of the regulatory division at the Department of Water Resources. And so as I mentioned, I manage the dam safety program, and then Aaron Carranza is the director of the regulatory division. So one of the main sections of North Dakota Century Code that we work with is section 61-16.1-38, which requires a permit to construct or modify a dam, dike, or other device. And we'll talk about what that means here in a minute. Then also North Dakota Administrative Code, section 8908, also provides regulations for dams, dikes, and other devices. And within the DWR's regulatory division, we have the dam safety program, and we also have an engineering and permitting section. And so these sections of code, they both talk about dams, dikes, and other devices. So we have it divided up where with the dam safety program, we're dealing with dams and ponds, and then dikes and other devices are dealt with by our engineering and permitting section. So definitions are given in North Dakota Administrative Code 89080101. And in that section, it defines dam as any barrier constructed across a watercourse or an area that drains naturally to impound or attenuate the flow of water. And the top photo there is an example of what we mostly typically think of when we think of a typical dam. Dike, on the other hand, means by definition, any artificial barrier constructed along a watercourse or area that drains naturally to divert the flow of water to protect real or personal property. And those are permitted, as I mentioned, through our engineering and permitting section, but they're kind of outside the scope of what we're discussing today for the most part. And then other devices is defined as a water control structure other than a dam or dike, including diversions and holding ponds, lagoons, or dugouts. And so, like Eric mentioned, sewage lagoons, and then holding ponds, like the lower photo. That photo is an example of the type of pond we see, for example, out in the western part of the state in the oil industry, that they build sometimes for water supply, for fracking and that sort of thing. And so sometimes ponds can be, excavated below grade, and sometimes that's what we might think of. But a lot of times they'll have an embankment built up above grade around the pond that's holding water, that is acting as a dam, that's exactly the same as a dam. And sometimes those embankments can be pretty significant. And so those are permitted and treated just like a dam would be. Oops. So per Century Code, construction permits required to construct or modify a high or medium hazard dam that stores more than 25 acre feet of water, or a low hazard dam that stores more than 50 acre feet of water, or if you have a pond or lagoon, if it stores more than 50 acre feet of water. And we'll talk in a minute about what is meant by low, high, and medium hazard. But those volumes are measured to the top of dam or to the top of the embankment. So low, medium, and high hazard are what we call the hazard classification, and those are defined as well in North Dakota Administrative Code. And what that refers to, it's looking at what's downstream of the dam, basically what's going to happen if that dam fails, what's going to be impacted. Is there potential for a loss of life? Are there homes downstream? Are there main roads or other infrastructure? It has nothing to do with the condition of the dam. It's strictly based on what's downstream. And these definitions that are written here are what are currently in administrative code. And I guess as a side note, the DWR is working on updating and modernizing these definitions, and those potential changes to admin code are out for public comment, and that's on the DWR's main homepage. You can go and look at that. But right now there's approximately 3,300 dams in North Dakota's inventory, and of those, there's 111 that are currently classified as high hazard or medium hazard. And just as a side note, our whole dam inventory is available out on the DWR's map service webpage, and the address is given there. And if you go to that website, you can pull up our dam inventory. If you go in the toolbar on the right hand side there, you can turn on the dams layer under water resources, and you can see there's all kinds of other helpful layers too. There's a lot of information on that map service. But so if you are building a new dam, or if you have an existing dam where you're doing, you want to modify it, maybe you want to raise it, or you want to do a modification, say you're doing a major repair where you're changing the spillway to something different or something like that, you'd want to apply for a construction permit. And to do that, you'd need to fill out the application form that's shown there. And then you need plans and specifications that must be completed by a professional engineer registered in North Dakota. That's required per Century Code as well. The only exception to that is if the dam is both low hazard and less than 10 feet in height. And you'd also need appropriate design documentation from your engineer documenting the analysis that they have done, and then evidence of property rights and in compliance with DWR's water management policy, which basically you need to own the land where the dam sits and the reservoir. You either need to own that land or have an easement, basically. And those documents that I've referred to are out on our website at the address that's listed there. So a couple of things that I just wanted to touch on real quick. They're kind of outside the scope of this discussion, but I know some of our engineers are on the workshop today, and so I just wanted to make people aware of a couple of things. One of them being the study that was completed last year. So this probable maximum precipitation, or PMP study. What that is, so probable maximum precipitation is talking about extreme rainfall events. It's the theoretical greatest amount of rainfall, or well, not theoretical, but the greatest amount of rainfall that the atmosphere can produce at a given location at a given time of year. And so this study updated those values for North Dakota. They're used in dam design and sizing your spillway. And in February, we published this interim guidance for using that study. And it has in there the implications on dam design that engineers can reference if they're working on a dam. So I just wanted to make people aware that this exists. And the other thing, some people on the workshop today might be familiar with this North Dakota Dam Design Handbook from 1985, and a lot of the content in this is out of date, and we're working on updating this. Hopefully that'll be pushed out for public outreach, within the coming year. That's underway as well. So if you build your dam, then following construction, North Dakota Administrative Code has a few requirements as well once construction of your dam is complete. One of those is that you notify the DWR of completion of your project within 2 years of your permit being approved. And what we do when you get a construction permit, we send out a form, a completion form that you can just fill out and send back to us with some basic information, letting us know that, yeah, it's been completed. And then another requirement is for as-built plans for the project that should be sent to us within 6 months of completion. And what that is the plans for the project showing any changes or anything that occurred during the actual construction marked up on those plans. So it's the final record of what was actually built. So that's important for us to have that, and for the owner to have that as well, for a record of what was actually built for their dam. And then North Dakota Century Code 6103-25 requires emergency action plans, or EAPs, for medium and high hazard dams. And we'll talk more about that one in a minute. And so I've been kind of talking about the construction permit. Your project might need some other permits from the DWR as well. The water permits are managed by DWR's Water Appropriation Division. If you have a dam, there's a good chance you're going to need a water permit as well. Those are generally required if a dam stores more than 12.5 acre feet at the normal pool level. It's probably going to need a water permit to store that water and put it to beneficial use. So we anytime somebody talks to us about a construction permit, we direct them to our Water Appropriations Division as well. And then sovereign lands permits, those are managed by our regulatory division as well through our sovereign lands program. And that applies if your project is located somewhere where it's on sovereign land, a river, generally a river, like maybe the Souris River or the Cheyenne River, someplace like that that's sovereign land. And there might be other permits, of course, by other agencies as well that might apply. Okay, so the emergency action plans, so what that is, it's basically a document that gives you some direction on what to do if there's an emergency at your dam, with notification charts, phone numbers, contacts, inundation maps showing what's going to be affected if the dam fails, a plan of action of what to do in an emergency. And so North Dakota Century Code 610325 requires that the owner of a higher medium hazard dam develop, periodically test, and update an EAP for their dam, and that the EAP and subsequent updates be submitted to the DWR for approval. And later today, Eric will have a whole section on EAPs, talking about how to develop those and what should be in them and everything. So that'll be good. Stay tuned for that. Century Code 610321 also requires operating plans. If you're an operator of a reservoir with a capacity of more than 1,000 acre-feet, it requires that you file an annual operating plan with the DWR. And so if you're the owner of a dam in that category that stores more than 1,000 acre-feet, you should be getting a notice from us each year. Century Code notes that those are due by February 15th. So we've been sending those out the early part of the year, and we started sending a little form that people can send back, trying to make this easy to comply with. And then the last thing I wanted to just touch on, we get requests or questions from time to time on what's required to breach or remove a dam. And we don't require a permit per se, but there is a notification form that we have that's out on our website there, and just asking for basic information about what the project entails and what the plan is. And I guess one key point on that is that we ask people to ensure that that enough of the dam should be removed, and taken down to the stream channel elevation, so that it's not storing water anymore, so that it's not capable of storing water, so that there's not a dam there anymore, so that it's truly breached or removed and not storing water any longer. So that's all that I had, unless there's questions for me now, or you can certainly contact me anytime if you think of questions or want to talk about things that I didn't cover. So thank you.
Hey, Karen, this is Tim Dodd. I did think of one question, just wondering if the revisions to administrative code are going to bring those changes more similar to what the FEMA hazard classifications are.
Yes, that's exactly the intent. Correct.
Okay. Sounds good. Thank you.
Anything else for Karen? Okay. I guess first of all, does everyone see session 3 dam failure modes and case histories?
Yes.
Okay. I have about 10 after 11 my time, 10 after 10 your time. Rather than just jumping into this for 5 minutes, why don't we take our morning break now? But I would like to keep the break to just 15 minutes because we do have a lot still to cover. So I will start up on session 3 at your time of 10:25. Does that work for everyone?
That works.
Okay. All right. I'll be back in 15:25. So I am going to get started. Just to make sure, can you hear me?
Yes, you sound great.
Excellent. Okay. So we are now on session 3, dam failure modes and case histories. We'll be covering in this session how dams work, a little bit of basic dams 101, the many ways the dam can fail, circumstances that can make your dam fail. We're going to cover some key case histories of dam failures, finish up with how to gain access to the 5-day forecast information from National Weather Service, pretty straightforward. And then hopefully recognize at the end that properly maintained dams are less likely to fail. Some of the dams 101 principles of dam construction and operation, how dams fail, and then options to repair dams. Various dam components, we've, I think, covered most of these in the first session. Again, it's a typical earth embankment. It's got a 2 spillway system, a principal riser structure in the spillway, in the reservoir, equipped with a trash rack. We talked about some of those details. While you have a trash rack, then a secondary or auxiliary or emergency spillway, again depicted here on the left abutment of the dam. I think the only additional element here is we're showing a berm on the downstream slope. It's this area right here. Essentially, it's a downstream slope would continue up, and then there would be a horizontal section, maybe 8, 10, 12 feet wide, and then then the downstream slope then would continue up to the crest. The berm, putting a berm on the downstream slope does a number of things for you. One, it improves, this probably the most important thing is it improves the stability of the downstream slope. Ideally, the embankment should have an internal drain system, like we've talked about, an internal chimney and blanket drain. If it doesn't, the phreatic surface is likely to be extending out more towards the downstream toe or even out on the downstream slope. Adding a berm just adds additional weight, additional material that adds weight to that downstream toe that helps improve the stability of the downstream slope. The second thing it does is it provides access to the downstream slope. Certainly on higher dams, there's a benefit to having that horizontal, top of the berm. That you can get vehicles out there that may be helpful for maintenance activities, perhaps reading instrumentation, that sort of thing, and it also help in keeping the grass cut. Breaks up the slope, so it's a little bit easier for the people doing the maintenance and grass cutting to cut the grass. The third thing it does is just normal stormwater runoff coming down the downstream slope. Again, for higher dams, the runoff can build some velocity and start to erode the downstream slope. So by incorporating a berm, that stormwater flow obviously gets broken up. It comes down the upper part of the downstream slope, then obviously gets slowed down quite a bit when it hits the berm, and then sort of starts again from zero velocity, if you will, as it continues down the lower part of the downstream slope. So downstream berms provide a number of benefits. Typical cross section through embankment. I think we talked about most of these elements already. Top of the dam, your spillway crest. Spillway, at least the principal spillway will establish the normal reservoir level. If there's a secondary or auxiliary or emergency spillway, then that establishes your flood reservoir level, your maximum reservoir elevation, and then freeboard is the dimension from that up to the top of the dam. I think the rest of it's pretty self-explanatory. Here, again, is a cross section. Looking the other way, the reservoir here is on the right-hand side of the cross section, illustrating that phreatic surface. So once a reservoir is in place, seepage will come through the embankment, start to saturate. Once it reaches equilibrium, there is what's called this phreatic surface. It's the area or the contact between the soil that is fully saturated, meaning that the voids are fully filled with water, below the phreatic surface. Above the phreatic surface, the soil is dry or just slightly moist. Dry or slightly moist soil has more shear strength than the saturated soil. So ideally, the phreatic surface you want down deeper into the embankment. The best way to do that is either some type of internal drain system or creating a zoned embankment where you have a central impervious core. I talked about the zoned embankment. In fact, the next slide is going to illustrate that. This is an illustration of what's termed a homogeneous embankment. So the entire embankment cross-section is constructed with the same material, meaning that the permeability of the material is the same across the entire cross-section. This is that illustration of the zoned embankment where you have the central core of finer grained, much less pervious material in the center, surrounded by coarser material that's termed the shell. It is what happens as seepage comes through a much more fine-grained material. The phreatic surface will just drop down the way it's shown here. So in this type of example, although it's good practice to put a drain system in along the downstream contact of that impervious core and the downstream shell, sometimes it's not needed because the phreatic surface drops down into the foundation like it's illustrated here. Different examples of internal drain systems and how they're laid out or configured. Apologize, the orientation of these cross sections kind of flip-flop, so it's sometimes a little confusing. The previous this previous slide here, the water was on the right-hand side of the embankment, so flow would be from right to left. This particular slide is flipped, so the water reservoir is on the left-hand side, so flow is from left to right. The dashed line is that phreatic surface. So the kind of the minimal effort as far as an internal drain would be just a toe drain, obviously located at the downstream toe, designed to intercept that phreatic surface, pull the phreatic surface down a little bit. Whatever seepage comes in there gets collected in that collector pipe and directed to an outlet point where you could put a seepage weir on it to monitor. The middle illustration is just the blanket drain, horizontal blanket drain. So you can see it's extending further into the cross section than the toe drain does above. So you can see the result is that it intercepts that phreatic surface further into the embankment section, into the cross section. So it pulls that phreatic surface even further down. So the result is that you get much more of the downstream slope that is dry or just slightly moist. So you get stronger, more stable material on that downstream slope. And then typically the most extensive type of drain system would be the combination of a chimney or vertical, near vertical section, then attached to a blanket drain. So chimney and blanket drain, where that chimney is located just about at the center line of the embankment. And there you can see that it intercepts that phreatic surface basically right near that center line, collecting, controlling the seepage, conducting it out through the blanket drain, and the entire downstream slope or shell material there is just moisture dry. So that is a well-designed and likely very stable embankment cross section there. Some examples again: earth fill embankment, well maintained, good grass cover, no apparent seepage coming through it. The stability of the embankment slopes is largely a function of the slope itself, the geometry, and then that phreatic surface that we've spent a fair amount of time talking about. Example of how a gravity dam gains its stability. Although you don't have gravity dams, concrete gravity dams in North Dakota, there are certainly concrete spillways on some of your earth dams that would have the same type of stability layout as what's shown here. Rather than it being a non-overflow section, it would be a spillway section, but they gain stability by virtue of the weight of the dam itself, and it has to resist overturning forces caused by the headwater, the water in the reservoir, and uplift any seepage under the dam to prevent overturning of the downstream toe, and then also prevent any sliding along that foundation. So again, just an example of a concrete gravity dam and gravity spillway. Now the functions of the spillway. We've talked about some of this already, that the spillways establish the normal water level, normal operating pool. They also, whether it's a single primary spillway or a combination primary and secondary spillway, they allow normal flows to pass through the reservoir to the downstream channel. The spillways have to be designed to be resistant to erosion because their primary purpose is to pass flows, either normal flow or flood flows. Like I said, all spillways have three components: a control section at the upstream end, conveyance section, and then some type of energy dissipation at the downstream end of the spillway, most often in the form of a stilling basin or plunge pool. And then, like we've shown several examples of combined spillway systems where you have a primary spillway and then a secondary or auxiliary or emergency spillway. Some examples here is an overflow spillway. It looks like the weir geometry is a OG type of geometry, that very efficient curved cross-sectional geometry of the spillway. Water is free to flow over this. Obviously, there's no gates controlling the flow. It's not being piped through any type of culvert or conduit, just a free overflow spillway. Here's an example of a spillway with two forms of energy dissipation. You can see those blocks that are on the downstream chute of the spillway. They break up the flow, aerate the flow, slow down the velocity of the flow, all intended to reduce the energy of the flow as it's going down that chute. But then there's also a stilling basin at the downstream end. These are the blocks I was referring to. So as water comes over the spillway, it's got to route its way through these blocks, which slows it down, it aerates it, all of which reduces energy, continues down into the stilling pond. Again, there's always water here, so that as the water over the spillway comes in, it impinges on this ponded water, loses its energy, flows out across this riprap sill, and then ideally has lost most of its energy so that it can flow down through the downstream channel without causing any erosion. Example of a secondary or auxiliary spillway, earth embankment. This is a grass-lined auxiliary spillway located on the right abutment of this particular dam. Other elements that most dams have or should have are drawdown facilities, intake outlet structures. Here, the purpose of these structures are to control impoundment levels. They're typically valved piping systems. They may be incorporated into the principal spillway. If you do have a principal spillway, it's usually easiest and most economical to incorporate them into that structure. The lowest intake point is usually located at the low point of the reservoir, which allows you to empty the reservoir if need be. And many times they're located in what was the former stream channel. Example of a concrete intake structure looks like it follows that standard SCS design that I mentioned earlier, where they have that trapezoidal top section with the horizontal trash rack bars. These horizontal bars, obviously the pool is quite down at this point. There must be a low level gate below the water surface, because this is a gate stem that's rising up to the top of the structure. There must also be some type of inlet at this level and on the opposite side, because this is another trash rack that's visible. So this would be a multi-level intake or outlet structure. Here is an example of one of those gates being operated. So going back to this, there would be a concrete platform on the crest of, on the top of this structure. So this gate stem would extend up through that top, and then there would be an operator like this orange one that would be able to crank open or close to open or close the gate. Another example of a low-level outlet, a little smaller scale. So here is just a free overflow spillway, conveyance channel, little runout apron. You can see on this right abutment of the spillway, here is a floor stand operator. So there must be a gate in this concrete chamber located on the right abutment of the spillway. So water will be able to flow from the reservoir into this concrete chamber. If the gate is open, it would then be allowed to flow through this pipe and discharge right here onto the spillway apron. And you know, the ability to lower the lake is important. Many state dam safety regs require it, certainly for high and medium hazard dams. You know, if there is some problem that's identified with the embankment. We're going to show some examples of these types of problems. It could be a slope instability. It could be excessive seepage coupled with piping, which we're going to show you some illustrations of in a few minutes, all of which could lead to failure of the dam. The best way, if these problems are identified early, the best way to prevent a failure is to initially start to lower the reservoir, take the load off the dam. And the only way to do that would be through one of these low-level outlets. So that's why they are so important to have, certainly on the high and medium hazard dams. Getting into different types of dam failures and why a dam failure is of concern. I think most of this is pretty obvious. Certainly the greatest concern is the potential for loss of life. Also for property damage can be extreme property, costly, high, extreme property damage. There's certainly an environmental impact to dam failures. Loss of use of the reservoir itself. So, if the dam impounds a reservoir for water supply, public water supply, or say hydropower generation, there is a real public need associated with the reservoir. So a dam failure would obviously take away that use of, say either public water supply or power. So that can be a huge impact. And then obviously the cost to reinstate the use by either repairing or replacing the dam. Potential loss of life, the concern is downstream, certainly for permanently inhabited structures, houses, where if the dam fails, if the inundation levels of the failure caused by the failure would get into the first floor of the house, there's a potential for loss of life. Certainly, even if there's areas that are not permanently inhabited, but places of work where people are there, certain hours of the day, schools, that kind of thing, it all presents a potential for loss of life. Again, then damage to downstream property. There's also the potential for significant infrastructure downstream that would be damaged during a dam failure, say highways, county roads or highways that might be needed for evacuation or movement of materials to rebuild or even try to prevent the failure of the dam. Those could be washed out. Railroads, significant pipelines, whether it would be water supply pipelines, gas pipelines, electrical lines, any type of utility that is downstream within the path of the failure could be lost. Impacts to the environment, certainly you could have significant erosion downstream, loss of vegetation. That erosion then would be deposited at some point in the downstream area into downstream water courses, not to mention the potential for loss of wildlife, all sorts of things. And then again, the loss of the reservoir use itself. Many ways a dam can fail. This is just a partial listing of what ways dams can fail during, in this particular instance, during extreme events. We'll talk about what those would be, but extreme rain events, earthquakes, that sort of thing. Dam can fail if the spillway capacity is not adequate to pass that storm flow. So this would be something during an extreme storm event. If the spillway obviously is passing the storm, but the materials are not robust enough and the spillway then starts to scour or erode, there could be internal erosion along conduits. This is the piping concept that we're going to illustrate just in a minute or two. There could be structural failure of either the inlet or the outlet works, either due to the increased loads from flood flows or also seismic earthquake loads, increased seepage pressures during both any extreme event, either seismic or hydrologic. During an extreme rain event can increase seepage pressures. Erosion from the uprooting of trees and woody vegetation. We're going to talk about why you should not have trees on an embankment dam. What that can blow over during, say, high winds associated with a storm event, wave erosion, and then liquefaction. Liquefaction ties into that concept of the phreatic surface and soils that are fully saturated. Soils being particles gain their strength by the friction between the individual soil particles. In a state of equilibrium, if the voids are filled with water, but the water is not pressurized in any way, then the soil particles are still in contact with one another, so they still have that shear strength available to them. But if the soil is pressurized, either due to, say, seismic waves or a storm event that raises the reservoir level, so now the water that's in the pores of the embankment dam feel the increased pressure due to the increase of the pool level, that then will reduce that friction or shear strength between adjacent soil particles. Eventually, if the pressurization of the pore pressure increases enough, the soil can go to zero shear strength, and it becomes liquefied, and hence the term liquefaction. So the water or the soil actually would flow like mud due to that liquefaction, and there's some examples of that coming up as well. So this is a graphic of the many causes of potential dam failure. Just in one spot, it sort of covers all of them. Starting at the upper left, if the dam is poorly maintained, so that the grass tends to grow, you start to get woody vegetation. Woody vegetation would then eventually grow into mature trees. The trees present a number of problems. The roots from the trees can create seepage paths. The heavy vegetation then harbors burrowing animal activity. So the burrows themselves can act to damage the dam. Plus, those animals like to have the safety of the overgrown condition of the dam. So it's hard to see any of those things. It also makes it difficult for engineers who are trying to inspect the dam to want to even get out on the dam and then see anything that might be going on, like cracks or surface movement, that sort of thing, or even seepage. So having the dam poorly maintained, heavily overgrown, can be a problem in many ways. Seepage coming through the embankment, we've talked about a fair amount already. Again, in the lower part here, this red circle showing the seepage coming out up the slope. This means that phreatic surface in this area is elevated to the point where it is exiting on the downstream slope, which means that the soils in this area are fully saturated, so they have lower shear strength than the drier soils around them. And if there is an applied load to those soils that are fully saturated, either by an earthquake or a storm that elevates the reservoir level, if the soil particles are sized a certain way, they could be subject to that liquefaction phenomenon that I described just a minute ago. I should say that not all soils are subject to liquefaction, even if they're saturated. The soil particle size has to be essentially relatively small, so the soil needs to be a very fine sand or a silt. It cannot have any plasticity, so it has to be a non-plastic silt or fine sand, and the soil particles all need to be right around the same size. They can't be well graded through a variety of sizes, but if the soils meet all of that, if they're relatively fine grained, non-plastic, all about the same size, then they can be subject to that liquefaction potential. Other problems, Transverse cracks, cracks that would extend through the embankment in the upstream, downstream direction. If they go deep enough, or if the reservoir level rises due to a storm, you could get water moving through that crack. Once water starts to move through the crack, it would start to erode the embankment and work its way down. A crack oriented that way might be a result of settlement of the embankment material or foundation. Settlement of embankment materials generally occur during or shortly after initial construction. All of the settlement will occur generally within the first several months or maybe year. So if the dam has been around for a while, this type of cracking is very unlikely. But the problem with transverse cracks is actually showing it here would be if that reservoir is elevated, water can flow through it and then cause a problem. If the reservoir level rises high enough, let's say the spillway is not large enough to pass the storm event, so the reservoir just keeps rising to the point where it overtops the embankment, that can lead to a failure. Same thing with the structural failure, some kind of slope failure, oftentimes tied to that phreatic line. Here, this internal piping, this internal erosion of the embankment. And we're going to actually show some animations over the next few minutes that illustrate all of these concepts really quite well. So the first animation is going to be this animation basically showing an embankment starting out in very good condition, well maintained, and then what can happen to it over time if it is not maintained. Let me just make sure, is everyone seeing this and hearing this?
We're seeing it. We didn't hear anything. So you may need to unshare and reshare and check that box to
Yes.
share the sound.
Okay, hold on one second. Yeah. Yeah, probably what happened was when I turned it over to Karen and came back to me, I didn't recheck that.
So that minor problems do not.
You hear that now?
Yes.
Okay, I'm going to start it back at the beginning. We'll start over.
Like any infrastructure, dams need to be maintained. Maintenance activities should be performed routinely so that minor problems do not become major. In humid eastern climates, vegetation will grow spontaneously. Unchecked growth of trees, brush, and long grass is undesirable for the following reasons. Trees can become uprooted, damaging the crest or slope of the embankment. Heavy vegetation will make inspection difficult and provide a haven for burrowing animals. Trees and brush can block spillways, reducing the dam's ability to pass large flood flows. Erosion of embankment surfaces is undesirable. Rainfall runoff can create erosion gullies, particularly where the dam meets up with the abutment. Burrowing animals should be controlled. Animal burrows will shorten seepage paths, which increases the potential for piping and internal erosion of embankment material. Sloughing and small surface slides can develop at any time. Surface slides need to be immediately repaired before they increase in size and become a major stability problem. Debris can block the spillway inlet, leading to increased pool levels and possible embankment overtopping. Riprap should be carefully inspected and replaced as needed. Wave action can damage the slope protection, exposing underlying embankment soil to rapid erosion. Debris left to collect on the upstream slope can damage the slope protection and hide problems. Keeping a dam in good condition is important and will prevent problems which could lead to failure.
Okay, and we do have a number of these animations that are really quite good in illustrating some of these concepts. So circumstances that can lead to a failure of a dam, certainly extreme natural events such as extreme rainfall, earthquakes, or high winds. Oftentimes, the rainfall, extreme rainfall events are coupled with high winds. Examples certainly include, hurricanes that we do see quite a bit off the East Coast. But certainly you're no stranger to large storms there in the interior of the country. The concern with a lot of the heavy rainfall is erosion from flood flow. Concern for overtopping erosion, overtopping of the embankment. We'll be talking about that. Foundation undermining, abutment erosion, and then internal erosion. This is the piping concept, either through the embankment, seepage through the embankment, seepage through the foundation, or preferential seepage paths, typically along penetrations, pipes or outlet conduits through the embankment are areas that oftentimes you see this seepage. Causes of flood flow erosion can be inadequately sized spillways, spillways that are blocked with debris, inadequate freeboard, which we've kind of talked about what that concept is, undermining of the spillway toe, or erosion of the actual spillway materials. Just to illustrate then some of these concepts. Inadequate spillway capacity, meaning that the spillway obviously is not large enough to pass the particular flood flow. So here's just a graphic of an overflow spillway down through the center of the dam. The spillway or the flood discharge is so great that it fills basically that spillway discharge channel and goes up and over the sides, the spillway sidewalls or the training walls, so that you end up getting overtopping flow over the embankment. And here is an example, a photograph of an earth embankment that is being overtopped. You can see the water flowing over the top of it. Even an embankment that's got a relatively flat downstream slope like this one appears to have, that is well maintained and has a good grass cover, cannot withstand overtopping flows. It does not take much depth or very long duration for erosion to start occurring. It typically starts at the downstream toe and works its way in the upstream direction, eroding up through the slope to the crest and working its way into the reservoir. Here's another animation that illustrates this overtopping concept.
Dams are designed to store runoff resulting from heavy rain. When storage has reached a specific limit, spillways are designed to pass the excess floodwaters, initially through a primary spillway. Many dams are equipped with an emergency spillway to help pass large flood inflows which exceed the capacity of the primary spillway. In an extreme flood, flows can exceed the combined spillway capacity, spill over the top of the dam, and create a very dangerous situation. Overtopping flood flows can rapidly erode down into an earthen embankment dam, leading to an uncontrolled release of the stored waters and causing catastrophic flooding downstream.
So some actual examples of overtopping. You can see the amount of erosion on that downstream slope. Another example of inadequate spillway capacity here. You can see the spillway, concrete overflow spillway right here. It did have some sidewalls. The flow was great enough that it filled the spillway, if you will, over the sidewalls, and then eroded the adjacent embankment section. The other problem would be you could have a spillway that is adequately sized, has enough capacity, but it becomes blocked with debris. Here's an example. You can see the spillway. Looks like it might be a gated spillway. It looks like there's some center piers with some superstructure, whether that's just pedestrian footbridge or maybe a bridge that will allow gates to be put in place. That's the problem with that type of design because of those center piers. If you have a heavily wooded drainage area, you can see the amount of debris that has accumulated in front of the spillway, which obviously reduces the capacity of the spillway. So the reservoir level continues to rise to the point where here it overtopped the left abutment of the dam and is actively eroding through that left abutment. An example of inadequate freeboard. Here is an access road coming up the downstream slope to gain access to the crest, all of which is good to have access to the crest for operation, maintenance, inspection requirements. But you can see that the road, as it gets up onto the crest, is actually at a little bit lower elevation. So it may have been constructed that way, or it could have been just due to the traffic that made it settle some, but there's now a low spot here. So whatever freeboard dimension was expected up to the top of the crest has now been diminished by this low spot. Example of spillway, downstream toe eroding very badly. You can see the side areas have eroded quite a bit, starting to undermine back under that concrete spillway slab. So if this is not addressed, certainly that erosion is going to continue to the point where the spillway slab starts to collapse down into the undermined area. This is an example of undermining of the spillway chute. This is a Mount Carmel Dam there in North Dakota. You can see that there's erosion of the soil adjacent to the spillway training wall as well underneath the spillway slab, the outlet channel slab. Here are some examples. All of these dams are in North Dakota. Here's Clawson Springs Dam. This was an event that occurred in April 2009. It was runoff associated with snow melt, which the flow started going through the auxiliary or secondary spillway and started to erode the spillway. The National Guard was brought in to try to halt the flow through the spillway. They were using helicopters to drop the large sandbags that you can see in the photographs to try to slow down or halt the flow through that auxiliary spillway. Here's another example at Cottonwood Creek Dam, the exact same time, April of 2009. It was the same event, essentially. It was snow melt. So these two events, these two incidents at these two separate dams occurred at the same time, which I'm sure Karen probably has some stories about, but when you have several incidents occurring simultaneously, it can stretch resources pretty thin. Here's just some more photos of the erosion at Cottonwood Creek Dam. You can see quite extensive. Here's after the water receded, the extent of erosion that occurred. If you can see, this is a man standing up here on the side slope. So you can see this erosion is probably a good 25, 30 feet deep. Seepage and piping. What is seepage and what is piping? Seepage is the movement of water through the earth dam or its foundation. It can be controlled or uncontrolled. I think I said at the outset that seepage through a dam by itself is not necessarily a problem. If it is controlled through internal drains, So it's collected by the drainage system and conveyed to the downstream tow. Then that's usually okay. If it is uncontrolled, then it can lead to erosion, internal erosion of the soils, which is a progressive type of event. Actually, will be an animation in just a minute to show that or illustrate it. But that uncontrolled flow can weaken the soil and cause ultimately a failure of the dam. And that internal progressive erosion is referred to as piping. It's defined as the movement of soil particles by that seepage water or percolating water leading to the development of these internal channels or pipes, where it gets the term piping. This movement or transport of particles leads to voids within the embankment. Got another of the animations to illustrate the piping.
Most all dams experience seepage to one degree or another. While the dam experiencing seepage may appear in sound condition, there may be damage occurring to the internal structure of the dam. If seepage flow rates appear to be increasing and the flow is not clear and is carrying material, internal erosion or piping is likely occurring. Piping is an erosion process that occurs inside the dam whenever the seepage flow starts eroding embankment materials out of and away from the dam. This starts at the downstream slope or toe and moves rapidly upstream to the impoundment. This process will tend to accelerate as the expanding larger opening or pipe allows for increased seepage flows. If left unattended, the seepage flow and progressive internal erosion will soon get out of control. When the internal pipe or void becomes large enough, the embankment structure above it will collapse. This will result in a failure of the dam's embankment and a potentially catastrophic release of the stored water, which may cause serious property damage and loss of life.
So some of the common causes of this seepage or piping would be poor construction, either unspecified materials used to construct the dam, or the material was poorly compacted, especially around penetrations, which would be those types of outlet pipes. Rodent activity can cause or lead to increased seepage or piping. And Anna Vargo contributed to the chat box that apparently there was a dam that failed in Utah that they believe was the result of animal burrows, which then during a storm event led to internal erosion due to the elevated reservoir level. So she's given us a link to YouTube. So I'm not sure I've seen that YouTube, but I'm sure it's probably pretty good. So at some point, folks should take a look at that. And thank you, Anna, for that. The other thing that can lead to seepage or seepage then causing piping would be tree roots. Again, if trees are allowed to grow and mature on a dam, and eventually if they die and the root ball is not removed, the roots will decay over time, and obviously the area that the root once occupied, once it decays, then becomes a void pipe, and then seepage can work its way through. Piping is a progressive type of problem. Initially, if it's caught early, it can be contained, but it can quickly lead to a full breach of the dam. This is a photograph of Teton Dam in Idaho. It was a dam that was owned and designed by the Bureau of Reclamation. At the time, the Bureau was considered, premier dam builders and designers. It filled during first filling. It was 300 and some feet high. Just to give you perspective, there's some outlet works buildings in the lower right. Along the crest of the dam, there was still a fair amount of construction equipment at the site because construction wasn't completely done, although they were filling it. So these are some large construction equipment running across the crest. And although it's hard to see, there are some bulldozers down on the downstream slope. This was an issue where they did not adequately grout the foundation rock in this right foundation, the abutment in the right abutment. So seepage was able to work its way through the abutment rock and then back up into the downstream shell of the embankment. It started, there's some earlier photographs, actually, this was all caught on camera. I think some tourists were visiting the area and happened to be out there with their camera and they caught this. So there's a series of photographs, but it started as just a little bit of a trickle, some seepage. Seepage over just about a 4 or 5 hour time worked its way up. The abutment contact, you can see obviously that's the downstream slope. This is the abutments working its way up. As the piping continues, the internal void starts to increase to the point where the dam actually it did collapse and create a full breach at that point where the dam was touching the right abutment. This was quite a shock at the time because the Bureau was, like I said, considered kind of the preeminent dam designers of the time. And unfortunately, there were 11 people that died due to the breaching failure of that dam. Smaller scale, here's an earth embankment dam. It looks like the reservoir level is up pretty high, so there's not a whole lot of freeboard, but you can see the seepage coming through the downstream slope and coming out really quite high on the slope. That obviously can lead to I'm sorry, that seepage to the embankment. If the seepage can pull fine grained materials from the embankment, it can cause that internal erosion, internal piping, erosion around these pipe penetrations. Any pipe such as the outlet pipe through the dam is a preferred seepage path along the outside of it and can carry fines with it as well. Here's an example of a dam, Dowd Dam in North Dakota, where piping seepage was flowing along the conduit and actually resulted in that sinkhole forming on the slope. Here's an extreme example, Nelson's Landers Dam, where the dam fully breached. You can see the outlet pipe here in the very bottom connected to the intake outlet structure there in the reservoir. So most likely there was not adequately compacted material around this outlet pipe or no filter diaphragm installed around the outlet pipe. So as seepage started to flow along it due to poor compaction, started pulling internal soil particles with it and eventually led to that breaching failure. Water exiting as a boil is a sign of seepage coming through the dam at relatively high pressure and velocity. So you can actually see the water roll, looks like it's boiling. And if you see an accumulation of fine grained material around that boil, then it's a classic example of the piping occurring. Eventually, as that pipe, if you recall in that animation, the erosion starts at the downstream end of the pipe and progressively works its way in the upstream direction to the point where it comes out of the reservoir. So if you see seepage boiling at the downstream toe, the seepage water itself would most likely be turbid or muddy because it's carrying that fine grained material. And if you see a corresponding whirlpool in the reservoir, and you've got a fully developed internal erosion pipe. So certainly the reaction would be to try to draw the reservoir down as quickly as possible, and most likely the EAP should be initiated, because if it's that far advanced, you'd probably want to have the emergency managers consider evacuating people downstream, because that's probably very close to failure at that point. Another mechanism is seismic load from an earthquake can lead to failure of an earth dam. Here's an example of a dam in California. The upper graphic shows the cross section of the dam. It's has a downstream berm on the downstream slope. There was a sizable earthquake that occurred that caused some of the soils to liquefy, so they lost their shear strength. So you can see the upper illustration is the cross section prior, the as constructed cross section, and then following the earthquake, the soils up here in this region lost shear strength, sloughed down into the reservoir. So you see the accumulation of that material in the upstream slope. But what it did was it left just a very little small pinnacle of soil retaining the reservoir, which obviously this would not last very long. Seepage would come through this quite quickly and result in a breaching failure. Earthquakes can also, that liquefaction that can cause slope movement that results in cracking visible on the ground surface. We also talked about wind either by itself or associated with a large storm. If you have a poorly maintained, heavily vegetated dam, the wind can blow the trees over, which then displaces a large amount of the soil, the root ball displacing a large amount of the soil, and that can lead to a failure. It's exactly what happened in this particular photograph. Other circumstances that can cause a dam failure include inadequate design of the dam, poor operation and maintenance, and vandalism. So how poor design failure or how poor designs can lead to dam failures would be that the spillway was not adequately sized. The embankment was not designed properly to either minimize seepage or collect and control it. The slopes were not designed to be, to result in stable slopes, or the proper precautions were not included or incorporated in the design to prevent erosion. And there was a number of different areas where erosion can occur. So you saw this graphic before. So this would be the same type of concept that would occur if the design was faulty, spillway was not properly sized. So during a particular storm event, the spillway gets overwhelmed, flow then extends over the embankment and overtops the embankment. Seepage through the embankment, again, if there's some problem with the design so that the seepage is not properly collected or controlled. Like I said, there was an internal drain system here at Teton Dam, but they didn't adequately address the potential for seepage through that right abutment. So seepage was able to bypass the seepage cutoff system and drains that were incorporated in the design. So seepage went under all of that and the foundation and abutment rock, and it came up in the downstream shell, which eventually led to the failure. Stability issues associated with the slopes, either upstream or downstream slopes, could be that the slopes were too steep to begin with. Either the design was faulty or maybe constructed too steeply. The high phreatic surface, I hope at this point now you have a good mental picture of what that would mean, that the seepage is coming through quite high in the downstream slope. So much of the downstream slope is saturated, which then could lead to slope instability, like in that particular photograph, or liquefaction resulting from a seismic load. But keep in mind, for liquefaction to occur, the soil's got to be a particular type of soil, non-plastic, fine-grained, uniformly graded soil. Another animation to illustrate these concepts.
One of the most serious dam safety concerns is the stability of the earthen embankment. Unsafe conditions could lead to a major slide that threatens the safety of the dam. A key factor to stability is the location of the phreatic line, or the fully saturated zone of the soils within the embankment. In safe dams, this level is well confined below the surface. Since soils that are fully saturated are not as strong, a higher phreatic line can reduce the ability of the embankment to resist sliding. This is often noted by seepage exiting on the downstream face of the dam. Weak or poorly compacted soils can increase both seepage and the phreatic level, as well as weaken the embankment, contributing to a sliding failure of the dam. Properly designed dams often include an internal drainage system, such as a sand chimney and blanket drain. They serve as a filter to keep seepage from moving any soil, as well as allowing seepage to be removed in a controlled fashion. This lowers the phreatic line and improves the stability of the embankment. For existing dams with a high phreatic line, two alternatives can improve the dam stability. One is to add a drain near the toe to both filter the seepage and lower the phreatic line through a controlled release of the seepage. The second is to add a berm for added resistance and improved stability of the embankment. This does not lower the phreatic line, but improves the dam stability by adding weight to prevent slides in the embankment.
Another way dams can fail is through erosion. Erosion of the spillway system itself or foundation of the spillway. So here is an example of, it was probably either poor joints in this spillway outlet channel, or maybe cracks that developed in the concrete outlet channel that allowed flow, spillway flow, to get down either through the crack or the joint and erode the underlying soil. This is actually a fairly common problem because certainly you can see the cracks, but if it's just joints that are maybe opened up or not properly water stopped or designed, it's just normal or typical spillway flow can get through those joints, or if there's a crack, the same thing. It can erode the soil, but you can't see that erosion because whatever material then just gets flushed downstream. It's progressive, so over time, the erosion void grows and grows to the point where then the concrete slab isn't supported anymore and just collapses down into the void. So you can see that this is a pretty catastrophic failure. Most of the material under that spillway slab had been eroded out to the point where most of the spillway has then collapsed into that void. Poor operation and maintenance can also lead to serious problems or even a dam failure. It can be either through inoperable gates that need to be used for emergency, burrowing animals, uprooted trees, plug drains, deteriorated concrete, or leaking outlet or low-level conduits. Example of outlet gate, a sluice gate that was never properly maintained. You can see the corrosion is basically the frame is completely rusted or corroded through. The gate stem is bent, so clearly that gate is completely inoperable. Here's one that again, you can see the gate stem in the left side of the photo is bent. The gate itself is popped out of the frame. So here this would have to be removed and replaced for the ability to lower the lake there. Here is a crest gate that failed, again due to some kind of mechanical failure that should have been identified through inspections and proper maintenance. Animal burrows can also lead to dam failure. Again, Anna had contributed information on that project in Utah. Here's an article about a dam that they believe failed, again, due to burrowing animals. There's a number of different animals that like to burrow and can create burrows in dams. Muskrats like to burrow in just under the water surface into the upstream slope. Beavers like to build dens or burrow also in the upstream slope. They generally like the protection that their entrances to the burrows are submerged that way, so predators don't have easy access to their burrow. Groundhogs or woodchucks conversely like to burrow in from the downstream slope. You can see some of the dimensions of these burrows, and they can be pretty significant. This is one of the concerns if you get burrows coming in on both or from both slopes. They don't necessarily have to connect, but they can get relatively close to one another, which creates a very, very short seepage path then that could easily lead to flow through those burrows, erosion, and then a possible failure. Uprooted trees we talked about, again, mature trees, if they get blown over, can pull up a large amount of the embankment soil, resulting in a large void that could reduce freeboard in this particular example, or just weaken the overall embankment. Example of just that occurring. Plugged drains. Certainly if it's an internal drainage system meant to intercept that phreatic surface, collect and control seepage. If the drains become clogged over time, then they're not going to be functioning, and then the phreatic surface will be allowed to elevate, and essentially the internal drainage system is not serving the function it's supposed to. So, drain outlets should be inspected for any type of accumulation of debris. They should have either covers or animal guards on them, so animals can't work their way up the drain to, say, put nesting material. And ideally, the drain should be televised on maybe a 5 or 10 year basis, depending on the age of the dam, so you can see the actual internal condition of the drain as well. Spalled concrete, here you can see exposed rebar, so there's pretty substantial loss of section. Once the rebar becomes exposed, it will corrode much more quickly, so the concrete will obviously start to lose its ability to withstand whatever loads can be applied to it. Problems with outlet pipes or conduits. Certainly any hole or crack in the conduit can allow seepage around the pipe to pipe earth materials into the outlet pipe, and then that just gets flushed downstream. So there's internal erosion can be occurring. You never actually see it happen until it becomes a big problem. If the joints become offset, either through poor construction or some type of settlement, again, the soils can be washed, the surrounding soils can be washed into the pipe, creating voids outside of the outlet pipe. Here's an example of such a thing where seepage was able to get into that concrete pipe through that open joint to the point where it piped that much of the embankment soil. Here's an example of the seepage along that outlet conduit, along the penetration. And like I mentioned a number of times, it's a progressive type of thing. So as the seepage continues pulling materials with it, that internal void can grow and grow and grow. And although this looks like it was caught before it led to a breaching failure, certainly it was probably pretty close. Vandalism and terrorism is always a potential concern, certainly for larger dams, and certainly ones that maybe serve either hydroelectric or water supply purposes. Terrorism, certainly became a heightened issue after 9/11, but even relatively recently, there was a man, Eric McDavid, who was convicted in 2007 for allegedly conspiring to bomb government and commercial targets near Sacramento, including their Nimbus Dam, which is the dam in the photograph, which he deemed detrimental to the environment. So he was obviously an environmental terrorist, was not able to carry out his ideas, but there are some people out there that have the desire to cause damage. Options for dealing with unsafe dams: you can repair the deficiencies, you can replace or reconstruct the dam, or possibly remove the dam. Options for repairing dams obviously depends on what the deficiencies are. If it is a spillway capacity issue, then you can increase the size of the spillway or add, say, auxiliary or secondary spillway on one of the abutments. You could provide overtopping protection, which is basically the construction of an erosion resistant material over the crest and downstream slope of the embankment, so that during the extreme storm event, water is allowed to flow over the embankment, over top the embankment, but you've now armored the embankment to be able to resist erosion and safely pass those flows. So you're essentially creating an auxiliary or secondary spillway over a portion or all of the embankment section. The permanent pool can be lowered. By lowering the permanent pool, you increase the freeboard amount, so you increase the flood storage capacity of the reservoir. You could perhaps raise the top of the dam, which would do the exact same thing, increase that freeboard dimension, which would increase flood storage capacity of the reservoir. Keep in mind, though, that to do that, you would need to make sure that you either own all of the land around the reservoir that you're now flooding due to the increasing the top of the dam, or you have some kind of flood easement for all that area. Or in some states, they allow you to justify a smaller design storm for the spillway, which generally is tied to what the hazard class is. If you can show that there is no increase in hazard downstream if the dam fails during a larger storm event, which allows you to perhaps reduce the cost associated with upgrading the dam, but there's still the chance the dam could fail during those larger storm events. So you have to weigh, and the analysis would show that you're not increasing any risk downstream associated with that failure, but you certainly would have loss of use of the reservoir. So you would have to weigh all that in. Another option is to intercept or control any seepage or leakage. If that's the issue in the seepage, that could be by installing some kind of tow drain, or try to install a chimney blanket drain and then putting a berm over top of it. You could improve the stability of the slopes if that's the issue, repair the concrete sections if that's where the deficiency is, and or repair or replace the low level outlet. Again, depending on what the deficiency is, these are the different types of repair options. As far as replace or reconstruct the dam, it could either be you'd have to lower the reservoir, empty the reservoir, remove the existing dam, and then construct a new one within roughly the same footprint. Or oftentimes, if that becomes an issue of emptying the reservoir, a new replacement dam can be constructed on the downstream side of the existing dam, assuming you have the property to do it. And then the existing deficient dam is either partially breached or removed, so that all that remains is the newly constructed dam. And then as far as dam removals, you could either do a complete breach, partial breach, or if the topography is right, you could try to bypass the dam altogether. Keep in mind the responsibility of the dam owner. The dam safety regulations require the dam owner inspect the dam on some regular basis. Inspection should be conducted after any major flood events, or actually any major natural event like an earthquake as well. The owner is responsible to take emergency action to protect the dam, report any major damage or changes in condition, and maintain the dam and operate the dam safely. Now I'm going to cover a couple key dam failure case histories. Are there any questions on what I've covered up to now? Okay. First case history is Buffalo Creek Dam. Just a little bit of background history. Majority of the dams in the United States were constructed in the 30s, 40s, and 50s, basically following the Great Depression, the general industrialization of the country. Following the Depression, there were a number of government programs that were instituted to put people back to work and build dams in the Midwest and western part of the country to help settle those areas. The dams were intended to provide water supply, irrigation water, hydroelectric power that help essentially settle some of the areas in the Midwest and far west of the country. So by the 1970s, many of the dams in the country were either 50 years old or approaching 50 years old. So they were starting to age. And the decade of the 70s saw a sharp increase in dam failures compared to the previous decades in the 50s and 60s. So in 1970 overall, and in particular 1972, there were quite a few dam failures. Buffalo Creek was one of those that occurred in 1972, and the failure did lead to the passage of Public Law 92-367, which created the National Dam Inspection Program. And that program basically gave the Secretary of the Army and then ultimately the Corps of Engineers, U.S. Army Corps of Engineers, the authority to begin an inventory and inspection of all the nation's dams. Although some states did regulate dam construction and have a fair record and history of the dams, many did not. So there was many dams built across the U.S. that were not built to any particular standards, were not built under any permit, and were not subject to any type of regular inspection. The law passed, however, it was not funded. So the law basically sat there in 1972, but the Corps was never able to start their work because it was not funded. Buffalo Creek Dam was in Logan County, West Virginia. It was part of a mining operation. So it was actually a tailings dam. And it was one of 3 impoundments. So it's a little bit hard. This is obviously an old photograph, but the 3 dams were in series up this leg of the valley. So dam number 1 was located sort of in this location, dam number 2, and then dam number 3 up here. The failure resulted in 125 people being killed, over 1,100 people being injured, and 4,000 people becoming homeless. So 4,000 or that many homes being lost, that 4,000 people became homeless. Buffalo Creek was one leg. There was also another leg of the creek here and a third leg coming down here. There was a small community at the confluence of the 3 legs here that was completely wiped out. And then Buffalo Creek continued down to the right lower corner of the photograph. They said Buffalo Creek was one of 3 coal slurry impoundments. They were located in a series. There was no formal design or engineering involvement in the construction of these, which was not uncommon for tailings dams, and unfortunately, actually for some other dams that are not necessarily tailings, but tailing dams in particular, oftentimes were just built by the men that were responsible for operating the mine. Intermittent inspections did identify deficiencies, so there's records of these inspections and the deficiencies that were noted, but they were never addressed. One of the main deficiencies was that there was no spillway structure that was included in the construction of the dam to pass any type of surface runoff. So again, these impoundments were intended to just take the slurry that was part of the coaling industry, let settlement occur. The water then would be decanted off as the settled material filled the impoundment. They would oftentimes then just add to the tailings dam, just raise it up. And it was a progressive type of thing that resulted in some of these dams getting fairly tall or high. But there was no spillway put in here to accommodate just surface runoff due to rainfall. The failure did follow 5 days of rainfall. It was a sequential failure. So impoundment number 3, which was the upstream-most impoundment, failed first, which then, added all that impounded water into the impoundment of number 2, caused that to fail, and then ultimately 1 fail. So all 3 of them did ultimately fail. Based on reports at the time, the failure was either overtopping or internal erosion. Initially, logic would make you think that it was probably overtopping since there was no spillway and they had 5 days of rainfall. You expect that the runoff would just fill up the impoundment to the point where the embankment would overtop and be an overtopping failure. But there was a number of recorded reports by people at the dam at various points leading right up to the failure. And although the reservoir or the impoundment did rise up close to the crest from some of the earlier reports, the reports that were made just within 10 or 20 minutes of the actual failure indicated that the reservoir was actually down several feet below the crest. And then reports around the same time from people downstream indicated flow in the Buffalo Creek becoming quite muddy or turbid prior to the actual breaching of the dam. So what that implies is that it was actually probably an internal erosion or piping failure, so that it was a result of the rainfall, the reservoir level rising. That increased pressure probably led to that internal erosion or piping, which worked its way back to the point where it released stored water through that pipe. That was the muddy discharge, lowering the reservoir initially, but the pipe enlarged so much that it did ultimately breach the dam. So it's kind of a complicated type of failure scenario. But unfortunately, the impacts were quite severe. 125 people died, 1,100 people injured, many became homeless. And back in 72, it was estimated at $50 million property damage. That's $1972. 17 communities were impacted in total, with 500 homes being wiped out. The lessons learned from this incident there's a number of them that high and medium or significant hazard dams should be designed to pass an appropriate design flood. Dams constructed prior to available extreme rainfall data should be reassessed to make sure that they have adequate spillway capacity. In this particular scenario, should have a spillway to begin with, and it should be adequately sized. Regular operation, maintenance, inspection of dams is important to early detection and prevention of dam failure. The domino dam failure scenario, which is multiple dams in series failing by the upstream dam failing first, overloading the next dam, and so on, do require special attention in how they're assessed. Dams of all types should be designed by a professional engineer who is properly experienced. whether they're tailings dams or any other type of dam. Dam designs need to be reviewed by competent professional engineers. Proper quality control and assurance during construction is vital. Dam inspections need to be performed again by competent and experienced people. And then the results of those or recommendations of those inspections should be addressed. Tree roots, abandoned pipes, and other penetrations in the dam can lead to failures. Upstream dam failures can fail downstream dams. So quite a few lessons learned from Buffalo Creek. If you recall, that was back in 72. The failure of that it was the failure of that along with a number of other dams in 1972 that brought a fair amount of public awareness to the issue of dam safety, enough to get a law passed, but not enough to actually fund the law. It was not until 1977 when Kelly Barnes Dam failed in Stevens County, Georgia. This was 5 years after the Buffalo Creek Dam failure. Kelly Barnes was located in Georgia, which is the home state of the then president, Jimmy Carter. So it was after the failure of Kelly Barnes that President Carter did approve funding to fund the National Dam Inspection Act, which gave the funds to the Corps to perform which are referred to as phase one dam inspections of all the dams throughout the U.S. This is a photo of the failed Kelly Barnes Dam. It was a 30-foot high, 38-foot high earth embankment located about a half-mile upstream of the Toccoa Falls Bible College. It was constructed on a site of a previous smaller wood and rock crib dams, and it was modified and raised over the years, and there were limited records of those modifications. The dam did have a 30-inch metal pipe as a low-level outlet. However, the slopes were heavily overgrown, vegetated with trees and brush. There was no record of any maintenance or inspection, which again, at that time was not necessarily uncommon. And the failure did follow a 4-day rainfall. Located between the dam and the college is Toccoa Falls, which was a 186-foot high waterfall. So the overall drop in grade from where the dam is to where the college is or was quite significant. Because of that drop in grade, the water from the breach discharged downstream with tremendous power and velocity. It did result in 39 fatalities, many of which were children and kids that lived in the dormitories. Lessons learned, many of the same lessons that were learned from the previous dam in West Virginia, Buffalo Creek. High and significant hazard dams should be designed by competent professionals. Regular operation and maintenance should be performed. All dams need to have an operable means of drawing down the reservoir. Although there was a low-level pipe here, it was not operable and there was no one there to even operate it. Uncontrolled vegetation on and around the dam can hinder inspections and lead to serious structural damage. And we've talked about why all that's a concern. Dam inspections should be performed by qualified people. Existing dams should have the original design reviewed as part of the dam safety review. Modifications to dam structures should be reviewed. And that is oftentimes a problem with older dams. They have been modified over the years, and sometimes the records of those modifications are sketchy. So you don't have a good understanding of what was done. And tree roots, abandoned pipes, and other penetrations can lead to failure. So many of the same lessons that we learned from Buffalo Creek. Now jumping up to more current events, and many of you probably remember this, Oroville Dam and spillways in California. This was only 5 years ago. Why this is important: Oroville Dam is 770 feet tall. It is the tallest dam in the United States. It's owned and operated by California Department of Water Resources. It's a key component of their state water project and supplies 23 million people with water. And it is the largest state-owned water storage and delivery system in the U.S. So it's a very large dam. It's owned and operated by a sophisticated dam owner. And even given all of that, they did have significant and very serious problems occur 5 years ago. The dam has two spillways located on its right abutment. There is a primary or service spillway that they call it, which consists of a concrete chute. The chute itself is 3,000 feet long, 179 feet wide, drops about 500 feet to the river below. So quite a bit of gradient flow going down that chute. It's a smooth chute, so the spillway discharge can accelerate and develop substantial energy going down that chute. Adjacent, there's also 8 steel radial gates on the upstream end of that spillway, so they can close the gates and basically either stop flow over the spillway or use it to raise the reservoir level if they need additional storage. They can open some or all of those gates to let water down that primary or service spillway if they need to lower the reservoir or just control outflow. Next to that service spillway is an emergency or secondary spillway. It's unlined. It has 2 crest sections, an OG weir, which is about 50 feet high, and then it's adjacent to a broad crested weir section. Again, the OG is that curved weir section and cross section that's highly efficient. Both of those weir sections of that secondary spillway then discharge onto the hillside over natural terrain. So this is an overview of Oroville, looking obviously from the downstream side. So the main dam is to the right. This is the primary or the service spillway that they refer to. This is the service spillway chute that's 3,000 feet long, 179 feet wide. There's a series of gates at the upstream end of this spillway that can control flow through the spillway. And then adjacent to that is the emergency or auxiliary spillway. And you can see that flow over this spillway then would just flow over natural hillside down to the river at the bottom. In February 2017, flow in the service spillway reached a level about a third of the historical maximum flow. This is in February, so most of the discharge was due to snow melt from the surrounding drainage area. As I said, this is a sophisticated dam owner. The dam was inspected on a regular basis. Anytime there was recommendations that came out of the inspections, they were generally acted upon right away. But February 7th of 2017, that flow, which again was only about a third of the maximum flow, resulted in a sudden failure and dislodging or removal of some of the spillway outlet channel, which you can see in this photograph. Flow continued down the channel. The flow then flowed into this void, and it caused rapid erosion of the foundation and adjacent ground, which you can see. This is on the left side of the spillway as you're looking downstream, all of the erosion that's occurring. So not only the void under the spillway, but it's flowing underneath the training wall, and it's eroding this adjacent hillside. And you can see all the turbid water flowing down the hillside adjacent to the spillway. This erosion worked its way both downstream and upstream from the initial failed section. The concern for that primary spillway chute, the erosion of it, so the dam owners and operators started to close some of those spillway crest gates to limit the amount of flow going through that primary spillway chute. But by doing that, they caused the reservoir level to rise because you can continue to get snow melt. There's also some storms occurring in the drainage area. So they started to reduce the outflow through that primary spillway, figuring they'd let the reservoir rise to the point where it flowed out through the emergency or auxiliary spillway. As it turned out, this was the first time in the history of the dam, first time in 49 years, that the auxiliary spillway was actually activated. What they didn't expect was that flow, which was only about 4% of the design capacity of that auxiliary spillway, started to cause extensive erosion and head cutting of the natural hillside just downstream of it. So this is the OG section or portion of that auxiliary spillway. You can see flow going over it. This is the natural hillside, and you can see these erosion gullies working their way up towards that auxiliary spillway. So now the owners and operators were concerned that if they continued to let flow go out the auxiliary spillway, that head cutting erosion would work its way up, undermine the auxiliary spillway control section, and possibly then the OG section here has a maximum height of 50 feet. So it's substantially high. I guess maybe the maximum section's over here. So they were concerned that this erosion will work its way back, undermine, and result in a breach of the auxiliary spillway crest that would release maybe upwards of 50 feet, the top 50 feet of the reservoir, which would be a substantial amount of discharge. And obviously that much water rushing down that hillside, they did not know then how deep the erosion of that hillside could go. So they continued back and forth, opening the primary spillway gates to try to relieve flow over that auxiliary spillway, but that then obviously led to continued erosion of the primary spillway. So you can see how much of that primary spillway and that hillside adjacent to it did erode. The impact of this, luckily, just due to the hydrology, the extent of rain, and when it did eventually slow down in the reservoir, and then working back and forth between both primary and secondary spillways, this never resulted in a full dam breach or failure, but they did get to the point where they were so concerned about the stability of that auxiliary spillway and the primary spillway, they did evacuate 188,000 people downstream. Once the event was over, they quickly initiated a repair program, which lasted several years, and it cost over $1 billion to repair both that primary service spillway and the auxiliary spillway. And clearly it was one of the most serious recent dam safety incidents in the United States, given the number of people that were at risk downstream. Although, clearly proper management of the emergency did prevent the dam from breaching, but it did raise, it still does, has raised many questions about the state of practice right now on inspections and what you can see with just normal visual inspections versus a thorough review of design and construction information. Because what they found was that the inspections, the visual inspections that were conducted over the years were not able to identify the underlying latent problems with the foundation of that service primary spillway, but a thorough review of design and construction would have. Currently most dams rely on just these periodic inspections to identify deficiencies, and Orville has raised the issue that maybe that's not enough. So lessons learned, there's quite a few of them. Complete and thorough dam record is essential. Concrete line spillways are vulnerable to significant damage and potential reservoir breach if flows are not safely contained. Dam incidents and failures can fundamentally be attributed to human factors. downstream of constructed spillway exit channels. Spillway outflows can erode and even breach dam embankments. They saw that adjacent to the primary spillway and also downstream on the auxiliary spillway. They did have an emergency action plan in place, which they did use, and they found that it can save lives and must be updated, understood, and practiced regularly. Many earth cut spillways have been constructed in erodible materials. It can result in unsatisfactory performance. That's addressing the issue with that secondary spillway that had never really been operated before and obviously did not function as it was intended. Stability of the dam foundation and other geologic features must be considered during dam design. Again, the erodibility of that emergency spillway channel was not adequately assessed, and the foundation of the chute spillway was not adequately assessed. Timely warning and rapid public response are critical to saving lives, and intervention can stop or minimize consequences of a dam failure. So again, they were on top of the issue, thank goodness. And here is a list of other lessons learned, all of which are pretty important. We're just at 1 o'clock. I still have one more dam failure to go through, but you've made this presentation available to the attendees. Is that right, Jennifer?
Yes.
Okay. Well, I will just kind of gloss through this awfully quickly. This was even more recently. It was a series of 2 dams in series in Michigan, Edenville and Sanford dams, and they failed in 2020, so only 2 years ago. If this is available to you, I kind of let you read through, look at the photos maybe on your own during lunch. It was similar to Buffalo Creek in that Edenville is the upstream-most. Well, there's actually 4 dams in series here, but Edenville is upstream of Sanford. Edenville failed first. Its failure released water that then overwhelmed Sanford and caused the breach of Sanford. So it goes back to the domino effect. The failure of Edenville had to do with elevated water surface elevations due to storms, and the embankment did liquefy here. So this was an issue of a high phreatic surface that then was, additional pressure was applied to it due to the elevated reservoir surface. There is actually a video. If you put in Edenville in YouTube, you can actually see a video of this photograph here of the slope actually just sloughing down and kind of washing out. It's pretty dramatic. But Edenville then failed due to that liquefaction. The release of that water then went downstream. This is Sanford downstream. It is a gated spillway. Although the gates were fully open, you can see all the debris that accumulated upstream of the gates. So the elevation of the reservoir rose to the point where the right abutment overtopped at Sanford, and that's where the breach occurred, was in the right abutment. We do provide some overall details of the failure scenario. Impacts, luckily no one was killed, but 10,000 people had to be evacuated from 3 different towns downstream. 150 homes were destroyed, $200 million in damages. Both were hydroelectric facilities, although only Sanford was actually operating at the time. So there was loss of hydroelectric generation at Sanford, and the potential of it certainly for Edenville. And then again, a list of lessons learned that are worth reading through if you can, maybe while you're eating your lunch. Some conclusions from all of this. It's not necessarily if, but when flooding occurs at dams, because eventually all dams will be subjected to extreme floods. The ones that typically fare the best are the dams that are well maintained, well designed, properly operated, and protected to the extent they can be during the floods. You can minimize your liability as the dam owner by making sure that the dams meet all of the above requirements, that there's good and proper communication during any extreme event, and that that the dams are compliant with all of the regulatory requirements. Here's the website for National Weather Service that you can put in your zip code, so it can give you 5-day and even out to 15-day forecasts. There's also a storm prediction center there. And the website also covers 13 river systems in the United States. It gives you river levels and flow rates and that sort of thing. So that is all for session number 3. We're about 7 minutes over schedule, so we're going to break for lunch right now. I'd like to break for maybe about 45 minutes. So we try to get together maybe about 12:50 or 12:55. I'll get started again. And if there's any questions, I'm going to stay on live here for a few minutes if you have any questions. Otherwise, I'll break for lunch too. And then when we get started up again, obviously, I'll take a few minutes when we start if there's any other questions. And you can always type something into the chat box as well. So we'll take a break now for lunch. Thank you. All right, folks, we're on session 4, operation, maintenance, and safety inspection of dams. We will be covering dam operations, maintenance issues and activities, inspection issues and activities, and then highlight problems, typical problems with earth dams, spillway systems, outlet works, and then we'll touch on concrete problems, not so much maybe how they apply to concrete dams, but concrete spillway structures that you would likely have in North Dakota. Keep in mind the responsibility for proper operation, maintenance, and inspection of dams falls upon the dam owner. Operation and maintenance does pay off. Proper operation, maintenance, inspection of a dam is similar to an older vehicle or an older house in need of repair. If it's left unmaintained, obviously the repair issues tend to increase and escalate and get more and more expensive. Conversely, if you maintain a car or a house and repair it as it's needed, you will minimize the cost for those repairs. So some issues associated with proper operation of a dam. Record keeping is important. We'll talk about that in a little bit more detail. Periodic inspections and emergency action plan. EAP must be updated on an annual basis. Downstream development is typical, and it is potentially a concern that can drastically affect the EAP contents. As development occurs downstream, your hazard class for the dam can actually change. It can increase. It's a term we call hazard creep. If the dam was originally constructed years ago in a rural area, there may not have been anybody downstream impacted by a potential dam failure, but over time, as development occurs, those impacts can increase to the point where the hazard class might increase as well. Focusing on record keeping as a dam owner, the better documented you are on any and all the activities you perform around your dam, the better off you'll be if there's any issues that come up in the future. It's good to develop standard forms for inspections, for maintenance and repair activities, and any operation activities. Many times you can find these forms, standardized forms, in the state regs or the ASDSO information. The forms, obviously, the easier they are to fill out, the more likely you are to use them. You typically want to always record what the date and time is of whatever's being done. It's a good practice to record what the reservoir level is, what the weather currently is, and maybe any past recent rainfall. You want to obviously record what was performed, list any observations and or recommendations that are made from the inspection. Periodic inspections, we'll go over in a little bit more detail later in the session. The inspection frequency and format should follow whatever the state dam safety regulations require. And it's good practice to perform an inspection of the dam following any extreme event, such as heavy rainfall, a seismic event, or even a prolonged drought. Emergency action plans, they are covered in detail in the next session. Session 5, we'll cover EAPs. As Karen mentioned, they are required for all high and medium hazard dams in North Dakota. They should be updated annually. And hazard creep due to downstream development can obviously impact the contents of the EAP. We do have an animation that illustrates this concept of hazard creep.
Many dams were originally constructed in rural areas with little or no development downstream and were designed according to lower risk criteria. Over time, roads and homes are constructed. Years later, downstream growth can accelerate, with large-scale residential, commercial, and even industrial development taking place. In many cases, typical regulations related to the 100-year floodplain have not been rigorously enforced until more recent times. Breach inundation zones are typically much larger than the regulated 100-year floodplain, and much development has often occurred in the fringe area. In addition, dams that were properly sized for low-risk rural settings, even if well-maintained, are now significantly under-designed for the current high-risk urbanized conditions.
Okay, so continuing on different dam operation requirements, public safety around the dam and reservoir oftentimes depends on public use. Private dams, such as dams that are used for water supply and hydroelectric, in general, public access is, must be prevented or controlled. They don't want open public access to the dam and reservoir, and that will require proper warning signs, fencing, and other methods of preventing access. Public dams, such as ones that produce, recreational lakes, obviously you want to try to promote access, but you want it to be safe access. So again, there's proper warning signs and fencing to allow the public to get where they should get, but prevent them from getting in and around or close to dangerous areas associated with the dam. Example of public safety. Obviously, you do not want to allow people to be surfing down spillway, and most of these dangerous areas, any dangerous areas, should be have proper signage. There is a question. Should dam owners be in contact with planning and zoning of towns to discourage developments in certain areas, or is there not much a dam owner can do to influence development? It certainly never hurts as a dam owner to be aware of what's going on downstream of your facility. A lot of times, these planning and zoning officials do allow for public input, public opinion, public comment period. So, hopefully there is a format or a forum where you can provide your input. But certainly, if development is being carried out in accordance with the zoning laws that are in place, then there's probably not much more than just going on record that you can do to prevent it. But goes back to then what the zoning laws are. If they are not appropriate for, the area, then certainly, your activity at that level to try to change those laws is something that is a dam owner and a citizen you're able to do, or you have the right to do at least. But sometimes development, even if it's limited to, say, within the 100-year floodplain, which is pretty standard, if your dam is medium or high hazard, typically then the inundation limits would be the result of a flood greater than the 100-year. So that development downstream, although it would be in accordance with the zoning laws, still would be within your flood inundation if you have a high hazard dam, let's say. So unfortunately, there's not much that can be done in that case. That's a good question, though. Continuing on with public safety. Different methods to make the site as safe as you can from the public. The photograph on the left is a overflow spillway. At the top of the photograph is a boat ramp, boat launch area. So you can see that obviously the boats are being launched into the lake very close to that spillway because it is an overflow spillway. When you're down on the water, a low boat or a kayak or canoe, it is actually very hard to see that there's a spillway there. So there's a series of buoys, warning buoys out in the reservoir that are there with signs on them to alert anybody on the reservoir or pond of the hazards associated with that spillway. The photo on the right is a intake tower and an access bridge out to that tower. You can see there's a series of gate operators out on that tower. So there's multiple gates in that tower. So the owner of that facility obviously wants to prevent access out to the tower. Obviously, they wouldn't want someone to get out there and start operating the gates against their wishes. So additional dam operations to keep in mind: the operation of a bottom drain, siphon system, or gate and flashboard is important. So those mechanical systems, the drains, siphons, any kind of control gates, they should be operated at least annually to make sure that they are operable. They should be operated in a controlled manner. Any type of gate should be cycled into the open position and then closed, meaning that you might open it 25% of the way and then close it back down, open at 50%, close it back down, open at 75, close it back down, and then finally open at 100% and then close it. That way you're sort of just cycling it in small increments, allowing the entire mechanical system to take the load in an incremental manner. And if for some reason the gate doesn't want to close, hopefully in the first cycle, you've only opened it, say, 25%. So it's not fully opened. If the systems are deteriorated or have not been operated in many years, they should be inspected by a qualified engineer. Oftentimes they'd want to have an underwater inspection done by a diver to see what the condition of the submerged features are. And all the mechanical components should be lubricated according to the manufacturer's recommendations. Here's an example of a gate operator being operated with the control handle or crank. Additional dam operations may include monitoring fluctuations of pool level, the removal of floating debris. We've shown several photographs of debris that builds up in front of a spillway that obviously can accumulate to the point where it diminishes the spillway capacity. So if you're able to remove floating debris as you see it in smaller quantities, it's a little bit easier. If the dam has instrumentation systems, they should be monitored on some regular basis. Again, you might need an engineer to get involved to recommend what that frequency should be. Any kind of alarm or warning system should be monitored, and any kind of wildlife damage should be controlled. And again, we talked about what burrowing animals can do. Here's just an example of somebody taking readings in a piezometer. The blue thing in his hand is a water level meter. Essentially, it's a probe that gets dropped down into the piezometer. When it hits water, it triggers a alarm or beeping sound, and the cable that it's attached to has measurements on it, so you can read the depth down to the water level. Dam maintenance. A number of factors affect the type and frequency of dam maintenance, the type of dam, the function of the dam, watershed characteristics, the spillway system characteristics, and prevailing climatic conditions. Typical dam maintenance activities include nurturing and mowing of grassed areas. We talked about the crest and slopes of the dams. Dams should should have grass, and it should be nurtured so that it's a robust growth of grass to prevent surface erosion from stormwater runoff, but it should be cut on a regular basis so that you can basically inspect the embankment. Removal of woody vegetation, removal of floating debris from the spillways or outlet works, repair of any eroded or scoured areas. Many times these are areas that repeatedly see water or discharge. So as soon as there's scour or erosion noted, it should be repaired right away because subsequent rainfall events will continue to make the erosion and scour advance. And then control and repair any damage caused by wildlife. Details of nurturing and mowing grass areas, removal of trees and brush. Tall grass and brush make inspections more difficult. They also provide a haven for burrowing animals. So that's why grass should be maintained and cut regularly. Trees can be blown over in high winds, which can damage the embankment. The roots will penetrate the embankment and can affect the stability. And tree roots also then become pathways for seepage. So that's why woody vegetation should be removed from embankment areas. Here's an example of a mowing operation on downstream slope of an embankment. This is an example of a heavily overgrown embankment, trees, woody vegetation. They should be removed. Example of floating debris. You can see that actually there is a, I was going to say, it looks like there's some kind of boom extended across this water body to collect this debris, perhaps before it gets down to the actual spillway or dam. But obviously, as you start to get debris, it should be removed as quickly as possible so it doesn't accumulate. Here it is accumulated in front of a flood control inlet. There is a trash rack there doing its job, but then normal maintenance activities should be performed and remove that debris. Eroded and scour areas, I mentioned before, should be repaired as soon as possible to prevent progression of the scour. Wildlife activity should be addressed right away. Burrows should be backfilled as soon as possible. Beaver activity should be addressed. Many states, beavers are protected, so they have to be trapped and relocated, but they should be removed from the site. And obviously, if there's any dams built up, they should be carefully removed. So you also want to prevent wildlife from getting into drain pipes and outlet pipes. So some type of trash rack or guard is oftentimes used. And if there's dens or burrows, they should be excavated out and backfilled or filled in some way. Here's just an example of a embankment dam with a lot of issues on it. Obviously, a lot of trees that can cause problems getting blown down. We talked about the roots, will seek water, so they're going to penetrate down to the phreatic surface. They can become then seepage paths. animal burrows upstream and downstream, can short circuit seepage. So a whole lot of issues going on right there. Additional dam maintenance activities, opening and closing of outlet and spillway gates to ensure operability. Talked about they should be cycled if they haven't been operated in a while. They should be operated at least annually, if not maybe semi-annually. Any metal component should be painted, and mechanical components should be lubricated as required. Concrete joints or cracks should be sealed or grouted. Spalled concrete should be repaired, and any surface erosion on the embankment should be repaired right away. As we talked about, opening and closing of lake drains to ensure operability. You want to make sure that the lake drain is operable in the event of an emergency. All metallic components should be painted and mechanical components lubricated. Concrete problems on spillway should be addressed as soon as possible. Repair spalls. Embankment surface erosion should be, again, repaired as soon as possible, because any kind of subsequent rainfall will just aggravate those erosion gullies. So here's an example of an embankment slope being restored. Outlet channels should be maintained and stabilized if necessary. Warning signs should also be maintained and repaired, as well as instrumentation monitoring systems and upstream slope protection. So here's an example of an emergency outlet channel that certainly appears unstable. There should be some kind of erosion resistant material, either riprap or concrete, put in there to stabilize that channel. Here's upstream slope protection with riprap. If the riprap is decomposing, breaking down into smaller pieces, or if it was layer was thin to begin with, supplemental riprap can be placed in those areas. Oftentimes, if you get public access to the upstream slope of dams, you get fishermen that like to move riprap around if the pieces aren't that big, to create more comfortable standing or sitting area while they fish. But that moving the pieces around can result in sparsely covered areas or bare areas. So those areas would have to be repaired as well. Additional maintenance activities, removal of any sediment that gets deposited at intake areas, removal of diseased trees around the lake rim. That way you're sort of getting rid of the trees before they have a chance to fall over and maybe wash downstream and clog the spillway. Remove or controlling aquatic growth out in front of the spillways or intake structures. And then you want to maintain any emergency access routes. Moving on to dam safety inspection activities. Again, all dams should be inspected on some regular frequency. The purpose of the inspections is to assess the condition of the dam, identify any operation or maintenance needs. It's an opportunity to monitor instrumentation, and probably most importantly gives you an opportunity to identify the early warning signs of potential problems or potential failure. The types of things you want to look for while performing inspection would be the stability of embankment and any structures, areas prone to erosion, upstream slope at the lake level where you get some wave action occurring, or if the reservoir level fluctuates, you can get some erosion. You can have erosion on the downstream slope due to surface runoff. You can get erosion at the groin, the abutment juncture, due to surface runoff. And then at the outlet ends of any spillways or outlets, if there wasn't adequate erosion protection, then just due to the flows from the spillway or the outlet can cause erosion. You also want to look for seepage, whether it's through the dam, the abutment, the foundation, around any penetrations. Take a look at the vegetative cover, make sure that it's the right type and adequate. You want to look for any wildlife damage, and excuse me, and then also inspect concrete surfaces for any types of deterioration. So inspection activities on earth dams, embankment dams, looking for embankment slope stability, wave erosion, seepage, either through the embankment, abutment, or foundation, or woody vegetation growth. Here's obviously an example of a deep-seated slope failure. It's pretty obvious if you walked out and took a look at this, you knew there's a serious problem. A lot of times the problem starts with a shallow slope failure, just something small. It's pretty easy to see because when you have this type of material moving on the slope at the upstream end, you get a crack or even a little vertical face exposure of the underlying soils, and then you'll get a bulge of material here at the lower area. So even if they're just starting and relatively shallow, if you see a bulge and then a crack above it, it's an indication of some slope movement or slope failure. A lot of times if these occur very shallow but are not identified or observed, so they're left, initially it does not create any problem, but then the next rainfall, you get surface runoff coming down, water falling into this crack, saturating or further saturating this material that's already lost some shear strength because it's already sloughed and slid down. So you're further saturating it, reducing more soil's shear strength. So then a bigger portion of this starts to slide down. This is a vertical face, not stable, so some of that starts to cave off. So my guess would be this particular site probably started with some shallow slope movement like the other slide. It was never identified, and it was just over time that this was allowed to work its way back into such a large area and such a deep-seated failure. So that's why frequent inspections are important, because it allows you then to identify some of these problems early. This is relatively easy, relatively inexpensive to repair, and it is not an immediate safety concern. Whereas if it's left to this is a safety concern. The lake should be drawn down because this looks like a dam failure could be imminent, and certainly the cost to repair this would be pretty extensive. Wave erosion along the upstream slope, and it doesn't look like there was any riprap or any type of erosion resistant material placed here. And you can see that just over time, the lapping water will cut a vertical slope and continue to work its way through that upstream slope. So pretty easy to repair with just riprap. Embankment seepage. By now, you should have some idea of why this is potentially a problem, whether it's through the embankment or the abutment or the foundation. The concern is that if the seepage is muddy, if it's pulling fine-grained soils with it, you most likely have internal erosion or a piping problem that clearly, if it's left unaddressed, can lead to failure. Woody vegetation, overgrown embankment slopes. We've talked now a number of times about why that's a problem. Some additional inspection activities: wildlife damage, sinkholes, depressions, embankment cracking, sparse vegetation, surface erosion. Wildlife damage generally is visible from the evidence of the den. It's oftentimes pretty easy to see, especially if it's a new burrow, because the soil that they've removed is nice and fresh, usually stands out against the color of the vegetation around it. Obviously, the grass here is relatively low, so it's pretty easy to see this hole, this burrow. If the grass was real high, it would be quite a bit more difficult. So again, the reason to keep the grass cut down. Burrows on the upstream slope are a little bit more difficult because many times they come in below the pool elevation. So to identify those, it's a good practice to drop the reservoir level periodically if it doesn't normally do it due to the reservoir function. Just a matter of 2 or 3 feet, enough to inspect that upstream slope. And oftentimes you'll see the burrows just, a foot or 2 below that normal pool level. If you see a sinkhole on the dam, either the crest or the slopes, it indicates some kind of underlying problem, probably a serious problem. Should be investigated by an engineer for sure. The same thing with embankment cracking. Certainly one of this size should be investigated by an engineer. If it's a relatively new dam, it's probably due to some kind of consolidation or settlement of the embankment materials or the foundation materials. If the dam is an older dam, then the cause of cracking is a little bit more difficult to identify. Could be the result of some kind of seismic activity or some type of internal erosion, although internal erosion doesn't typically manifest itself like in a crack like this. Sparse vegetation, you can see obviously poor grass growth leads to just surface erosion. You get those erosion gullies, and then subsequent rainfalls, the water concentrates in those gullies and just makes them deeper and wider and progresses the problem. Vehicular ruts on the crest can reduce the freeboard dimension, can also allow for ponding water, which then just lets the water infiltrate into the dam. Best thing is to regrade the crest to a uniform elevation and create some kind of slope to it so that the water drains off one direction or the other. Some typical dam inspection activities associated with spillways. The common problems with spillways are erosion or scour of earth spillways, rock cut spillway, scour erosion, deterioration of concrete line spillways, or problems associated with the concrete spillway itself, cracks, spalls, that sort of thing. So this is an example of some erosion or scour of an earth spillway. This is Brabant Dam in North Dakota. You can see that it was an elevated water surface elevation. I'm guessing, given the partial snow cover, this is probably a late winter, early spring issue with runoff. Water coming down through the earth spillway and causing this pretty substantial erosion feature right here. Showed this example before, Cottonwood Creek Dam in North Dakota. This was a result of snow melt and some storms occurring in April. And you can see the extent of the erosion of that emergency or that earth spillway. Here is a spillway cut through the abutment on the abutment rock. And it does look relatively unstable. That whole that whole structure of the dam, the abutment, everything looks pretty questionable there. Here's a concrete spillway, concrete chute spillway. You can see the concrete is in very poor condition. There are quite a lot of spalled areas. Spalling is this loss of section of concrete. It's usually a result of freezing and thawing of the concrete. Tends to break up the mortar that holds the larger aggregate in place, and then just the hydraulic abrasion over the spillway tends to then work the coarse aggregate out of there, and then subsequent freeze thaw cycles will just exacerbate the problem. So you can see all these spalls. You can see vegetation growing in many of the joints and cracks. There's also cracks here. So as vegetation is allowed to grow, the roots tend to want to expand, which puts stresses in the concrete and can cause the concrete to spall and crack as a result of the vegetation. Here's, it looks like a section of concrete that's delaminated. Just really entire spillways in very poor condition. You can get undermining of the concrete slabs on the spillway outlet channel. This is a dam and also in North Dakota. You can see the amount of erosion under the chute spillway and adjacent to it. Common problems associated with the outlet conduits, undermining of the outlet, seepage along the penetration, joint deterioration or separation of the conduits or pipes that go through and under the dam, differential settlement along the conduit, misalignment of spillway conduits, and then spillway conduit deterioration. Example of inspection of a spillway conduit. Here you've got undermining of the outlet end. You can also see that the pipe is kind of squished down, so it looks like it had some issues associated with construction loading. But clearly erosion and scour at the outlet end. Example of seepage along the outside of the culvert or the conduit. Again, the concern with this is the piping of fine-grained soils from within the embankment. Joint separation of the outlet pipe. So there was soil originally above these sections of pipe, but over time, because the joints separated, that material was able to wash down into the pipe and flush out. So now you basically have a scoured or eroded area above the pipe sections. Misalignment of the conduit and the joints themselves. Again, if they're not aligned and connected properly, you can get soil washing in from outside of the pipe or the conduit, creating a void outside the conduit. This is an example of corrugated metal outlet pipe and how badly deteriorated corrugated metal can become. You can see the whole bottom third of the pipe is missing. So this is a problem with corrugated metal. Should really never be used within a dam. Many of these dams that do have outlet pipes that are corrugated metal eventually have to be removed or slip lined with another pipe material because the CMP will just deteriorate. I got a question from Dave. Let's cover that at the end of this section because I'm not quite sure what you're asking. So I don't want to forget about it. But when we get to the end of this section, if you can chime in, then we can see if we can answer that question for you. Inspection activities associated with concrete structures. Again, we're looking for deterioration of the concrete or any type of structural movement. Here's an example of pretty severe deterioration of a concrete chute. You can see the cracks, the spalls. It looks like it's penetrated the full depth of the concrete. So now you have voids occurring under this concrete slab or concrete channel. Just an example of a crack. Here's movement of a spillway training wall, probably associated with some type of erosion or undermining under the footing of this. This is a concrete gravity dam, but this would also apply to concrete spillways where you have loss of concrete on the surface, which is that spalling. You can see the exposed aggregate. And again, typically a result of freeze-thaw cycles. Concrete efflorescence, that you can see that concrete section of the wall. You have that random pattern cracking, and then that white material that's coming from all those cracks. It's usually a result of what's called alkali silica reaction or alkali aggregate reaction. It's a reaction between the hydration byproducts When concrete is mixed and it hydrates, there's actually a chemical reaction that results in the concrete hardening. Anybody that's worked with concrete knows that one, it generates heat. You can actually feel the heat of the concrete. That's a result of that chemical reaction. You can also burn your skin with fresh concrete, again, a result of that reaction. But certain minerals, certain coarse aggregate, if they have certain minerals in them, they can react adversely to some of the hydration byproducts. And the result is that a gel forms around each of the aggregate particles that has this particular mineral. And as the concrete continues to hydrate and harden, that gel material continues to grow. So the gel starts taking up space. It starts resulting in stresses within that mass of concrete. And then ultimately those stresses combine and cause this random pattern cracking to occur. And then the efflorescence is essentially sort of a self-healing as the concrete continues to harden. If moisture gets in it, those hydration byproducts will bleed out to the surface, and that is the white material, that white efflorescence that you see there. That is a structural problem, and ultimately there's nothing that really can be done about it. And over time, those cracks will continue to expand if they're exposed to air and water. And at some point, that section is just going to have to be removed and replaced. Here's an example of failed spillway training wall. It looks like maybe some seepage or flow came in off that abutment and obviously failed a section of the training wall. Seepage or leakage through concrete structures, whether it's a concrete dam or concrete spillway, generally is not a problem. Concrete through joints or cracks can withstand leakage through it. Typically doesn't erode concrete or anything like that unless there is active ASR, AAR, that alkali silica reaction or alkali aggregate reaction. And then the leakage basically continues to provide a source of moisture and oxygen, which promotes that adverse reaction. So that would be a negative. Gates, mechanical gates, they will again sometimes leak if water is not terribly valuable. If the rate is, seepage rates might be acceptable, but if it's in an arid region where the value of water is quite high, then the gate should be maintenanced and repaired to reduce the leakage. There's a number of information resources on the dam safety website. Here's a list of some of the different documents that are available that provide feedback. An owner's manual. They also have the impacts on dams due to plants and animals. All right, that is the end of session 4. David, can you put on your microphone and let me know what your question is? Because I'm not sure I understood it.
Well, I sent a photo over as well. So I've got a low-head concrete dam. And one of the problems that I kind of foresee with that is with the concrete structure being continuously underwater, we don't have any moving parts for it. Is there any good way to get a better idea as to the condition of that structure? Any thoughts, recommendations? Because otherwise all I can really do is walk around it and check to see if there's anything out of the ordinary, check the banks, check the riprap. I'm trying to think if there's anything else I can do in the inspection process.
Right. And it's low head, so it's kind of it's a run of river dam, so there's no way to
Yep.
really dewater it.
Exactly.
Yeah.
The photo I attached was from last year when I had probably about 6 inches going over the dam. That's about the lowest that I can get it.
Mm-hmm. Yeah, well, it's a good question, and you know that is it's an issue. It's a problem. If most dams obviously have areas of them that are submerged, and that is one of the problems with the standard visual inspection is that you obviously can't see submerged areas of a dam. In your case, it's the vast majority of the structure itself. So the first thing that comes to mind is you'd have to bring a diver in that can either, you know, at a minimum sort of feel around for, say, cracks or spalls. You know, if there's constant flow over it, it may be difficult for them to see. If they are able to see, then a lot of times they'll have video equipment attached to their helmets so they can do a video inspection. And if the water's clear enough, you can actually see something. But many times, all you're left with is their ability to sort of feel around, make sure that they're not feeling any you know, discontinuities or deterioration of the concrete, which would be just cracks and spalls or joints that have opened up, let's say. They can also probe the upstream side, or more importantly, the downstream side, for any scour or erosion of the riverbed that might be undermining the dam as well. Now, keep in mind that low-head dams do present a specific hazard on the downstream side, and if you know, most divers would be aware of it, but you know, you may make sure that if you do have a diver, that they are aware of it, that flow over a low-head dam can cause an undertow type of current that pulls people down under and into the toe of the dam. And there's many reports of people drowning because they've gone over a low head dam, and it might only have to be a couple feet high. I mean, you know, really small structures, but that roller bucket effect of the water on the downstream side can be dangerous. But if the diver can get in there safely, then maybe the really the only option to you is a diving inspection, which is not perfect, but it's something. You know, if there is a greater concern, maybe based on what a diver finds, then, you know, certainly looking at a more costly effort, but you could try to cofferdam sections of the spillway off to dewater sections of it so that you're still letting flow over the remaining length of that spillway. So you could break it into thirds or quarters to try to dewater it to get a much better look, but you're looking at a much costlier effort, you know, doing something like that. Did you get all that, Dave? Am I still live?
Yep.
Okay.
Appreciate the follow-up on that one.
Okay, no problem. Anything else from anyone? Been a relatively quiet group so far. Can only attribute that to my excellent presentation then. There's just no questions from it, huh? All right. Then we'll jump into session 5, developing and implementing emergency action plans, which we've talked about the importance and value of that already. Sort of check my time. I can put 20 minutes. Oh, I'm good with time. I think we've got plenty of time. All right. So what we're going to cover here in session 5, I'm sorry, I'm just taking a look at our timing, and operation and maintenance went awfully quickly. Okay, what we're going to cover here in session 5, we're going to define what an emergency action plan is. Karen's already touched upon that. We'll talk about typical components of an EAP and the development of the EAP. We have a number of learning objectives for this session. One, what the definition is of an EAP, the ability to identify the main components, identify steps required to develop an EAP, and then take corrective emergency preparedness and preventive actions during an emergency event at the dam. So according to
Hey, Eric,
yes.
we see your screen, but we're not seeing the slides.
You're not, the slides aren't advancing or anything?
We just see your main computer screen,
Okay, I'll stop.
but not the actual presentation. There you go. That
So
looks
you
good.
see Session 5, right?
Yes.
And then you see what will be covered, definition, components, development. Yep, you're still seeing this, right? I just now
Yes.
learning objectives. Okay, good. Okay, so that's I covered all those the objectives. So the emergency action plans for North Dakota, and Karen touched upon all this. Emergency action plans are required for all high and medium hazard dams in North Dakota. And the owners are required to, one, develop the EAP for their dam, periodically test the EAP, update the EAP, and then submit the EAP and any subsequent updates to Department of Water Resources for approval. Typically, you should look at updating the EAP on an annual basis, mainly looking for any changes in the personnel or phone numbers that are listed in the emergency action plan. So if it's not something that you update on an annual basis, certainly if you know there's been a change in personnel, at that point, the EAP should be updated. Conducting a test of the EAP, the most common is sort of a tabletop exercise, and the frequency of that type of exercise largely depends on the size of the dam, the hazard class, but usually you're looking at performing some type of exercise every couple years, maybe every 5 years. Again, if there's a turnover in personnel, say for the dam owner, it's certainly good to plan on doing a exercise or a test to get the new folks up to speed on the EAP and the contents. The EAP guidelines are available on the DWR website. That's where they discuss the format of the EAP, inundation mapping. They talk about the EAP exercises and updates. They recommend that the EAPs are updated annually, just like we talked about, and that an exercise is held once every 5 years. But again, if you know there's been a turnover in the personnel and the people responsible for activating and carrying out the contents of the EAP, it's always good to then do another exercise. North Dakota does have a recommended template for the EAP. The idea, most states follow this, where there's a pre-described format for the EAP. So it's actually pretty easy to develop one. Plus that way the information is pretty consistent from dam to dam, so that the emergency managers in the state that would be responsible for a lot of the work during an emergency, the plans are all similarly laid out. There's also a cost share available through the State Water Commission for the development of EAPs for eligible high hazard and medium hazard dams. And there's websites there both for DWR dam safety and the cost share program. Definition, can vary, some from state to state, but in general, the EAP is a formal document that identifies potential emergency conditions at the dam and specifies pre-planned actions to be followed with the intent to minimize property damage and potential for loss of life as a result of the dam failure and the release of the stored waters. So the idea of the EAP is that there's information in there for a variety of different types of potential emergency scenarios or events. The idea of the exercise is that everybody involved is familiar with the contents, and then during an actual dam emergency, as you can imagine, when emotions are high and stress levels are high, a lot of the thinking's already been done. The people involved are already familiar with the EAP document, and a lot of the pre-planning and thinking has already been done and put in the document. So all you really have to do is follow pre-described steps. So it does help to minimize the stress level of the situation, and hopefully result in an efficient response that can save lives and reduce damage. So the need for emergency action plan hopefully is self-evident, but regardless of the requirements for recorded or documented EAP by the State Dam Safety Program, every dam owner should consider and is strongly encouraged to develop some type of emergency action plan that could be used during an emergency at their dam. So like North Dakota, where the EAP is required for all high and medium hazard, sorry about that. I took a drink of water. Went down the wrong pipe. North Dakota requires all high and medium hazard dams, and that's pretty consistent among most states. There's a large number of low hazard dams that the regulations don't require EAP because they're low hazard. Hopefully there's no potential for loss of life, but certainly there's the potential for property damage, some property damage, and the loss of use. So it is strongly encouraged that all dam owners have some type of pre-prepared emergency action plan that they can rely on in the event of emergency. Again, I apologize for that interruption there. So run for it is really not an adequate emergency response. The pre-planning is what helps people get through the stressful event if it actually happens. The components of emergency action plan, and again, this is more or less kind of standardized now among most states, and like North Dakota does have a standardized template. Most EAPs contain some description of the basic characteristics of the dam. There may be an overview of the plan. It will list and describe what the roles and responsibilities of the various participants are during an emergency. So you would typically have the dam owner, you would have emergency management officials responding from downstream municipal entities. You may also get emergency management officials from county level entities as well as the state. You would also have dam safety involved, and you'd also likely have your own consulting engineer may be involved. So there are, the EAP would list these different entities and what their various roles and responsibilities are. It's going to describe event detection, and we're going to go into some of that detail just in a few minutes. The determination of what the emergency level is, basically how serious of a situation you have. It's going to list notification and communication with a notification flow chart. And that's where there's going to be actual names and phone numbers listed of key individuals that get contacted in the event of an emergency. And it's that information that needs to be updated either annually or when you know there's been a change in personnel. There's going to be a list of expected actions depending on what the emergency is. Then there's a section on termination once the emergency has subsided. Hopefully either it's been addressed or unfortunately, maybe if the actual dam failure does occur, at the end of all that, there is a formal termination. There is a section on EAP maintenance as far as review and updating it. And then there's a variety of appendices included, which would typically include the flood inundation maps, which are maps that are developed, would have to be developed by an engineering consultant. Engineers will use various computer programs to model the flood inundation levels downstream with and without a dam failure during different flood events. So typically one of the scenarios that's mapped as part of the inundation maps is a sunny day failure. This would be a failure of the dam not associated with any type of rain event. So there is no, there's no excess flow coming through the spillway. There's no base flooding downstream due to this rain event. In other words, it's just a sunny day, normal flow conditions, and then obviously something awful's happening at the dam and results in a breaching failure of the dam. An example of that might be that internal piping. Piping can occur not as a result of any flood flows. So in this particular example, the sunny day flood breach is shown by this kind of fluorescent green line. So there's a pair of lines, one on each side of the stream. So the stream is right down through here. And then you see the fluorescent green on either side of that. The sunny day breach then is basically just modeling the limits of flooding due to the release of the stored water, the water behind the dam at normal pool. So logic tells you that that's the smallest or the smallest area of inundation downstream. Then what most states require the engineer to look at is whatever the design storm is for the dam. So let's say it's a high hazard dam. And Karen mentioned that there is a state-specific hydrologic study being performed or has been recently completed there in North Dakota. And what they're looking for is establishing rainfall throughout the state during what's termed the probable maximum precipitation, the PMP. So most high hazard dams are required to be able to pass the flood that's the result of a PMP storm on their drainage area. So this dam break model is performed both looking at what flood levels occur downstream with the PMP occurring and no dam failure, and then the PMP with the dam failure. So in this particular example, you've got the fluorescent green, which is the sunny day failure. Then a little bit further out are a pair of lines, a navy or dark blue, and then sort of a red dash line. The navy blue is just that design storm. In the example I was giving, would be the PMF routed downstream, and then the red line would be the PMF with the dam break on top of it. And you can see how close, in this particular example, how close those two lines are, which indicates that the PMF by itself is causing the vast majority of the flooding downstream, and the unfortunate event of a dam failure on top of it, although when it's all said and done, there's going to be a loss of use of the dam and reservoir, the dam failure itself really is not causing any increase in risk downstream, because those two inundation lines are practically coincident. They're practically on top of each other. So the failure of the dam in this particular example is not really increasing dam impacts downstream compared to just that extreme storm occurring by itself, at least on this one page of the inundation map. You can see in this particular example, on the right-hand side in the legend, there's a key map. So the inundation extends quite a bit downstream. This is just one of a number of maps that illustrate that those inundation limits. So on this particular segment of the river, like I said, the failure on top of that extreme storm really did not increase the risk or the limits of flooding downstream. These inundation maps then are made part of the emergency action plan, and then these become a basis for the areas that the emergency management officials that are involved in these incidents, these become the basis for their evacuation areas. So part of these maps, in addition to the actual inundation limits, major roads and highways are labeled. In this particular case, you can see running left to right, there's a I-78, which is a major roadway. Smaller roadways should also be labeled. Some of them are, but actually they're hard to read with the background in this particular map. If there are key critical like infrastructure facilities downstream, pipelines or power plants, or say schools, elementary schools, or a hospital, a retirement type of home where you might have a large number of people that are not terribly mobile. All of those should be highlighted on these maps so that the emergency management officials can clearly see the areas that may need to be evacuated, and also maybe allow them to prioritize some of these areas based on what the use is. Keep in mind that the owner's EAP responsibilities, you're first responsible to develop and maintain and exercise the EAP. Once you have developed it, it is your responsibility then to distribute it to those emergency management officials that are downstream that would be part of the response if there was a problem. You're also there, well, I should say the technical sections of the EAP, such as those flood inundation maps, although it's your responsibility to get those prepared, you would most likely need to have a engineering consultant on board to develop them. You also might elect to get the engineer involved in the preparation of the EAP to emergency detection section, come up with evaluation, classification of potential dam failure incidents, and preparedness and prevention actions. So although some of those are prescribed already in the standard format, it may be a good idea to get an engineer involved in making sure that they're specific to your particular dam. You want to make sure that obviously the EAP contains all the above components. The EAP must be developed in coordination with state and local emergency management agencies, and it must also comply with all state dam safety program requirements. So those are your responsibilities as a dam owner relative to the development and keeping the maintenance of the emergency action plan itself. Probably your most important responsibility, though, is the early detection of a problem. As the dam owner, you're the person or your people that are around the dam most frequently. You're most familiar with the dam, so you're in the best position to identify a problem as it's occurring, hopefully identify, detect it early on so it can be addressed before it leads to a dam failure. But that early detection is perhaps one of the most important responsibility as the dam owner. So this event detection is just that. It describes the detection of an unusual emergency event and provides information to assist the dam owner in determining the appropriate emergency level for the event. But again, as the owner, most familiar with the dam, most frequently around the dam, that event detection falls onto you. So event detection is dependent upon observations at or near the dam. It may also be the result of evaluation of instrumentation data, could be the result of earthquakes that are felt or reported in the vicinity of the dam, and the forewarning of the conditions which may cause an unusual event or emergency event at the dam. As an example would be the forecast of extreme weather or flooding. So that could all lead to the detection of an event at the dam. So the lowest level of the emergency would be, say, level 1, considered a non-emergency, although it's a result of an unusual event. And whatever it is, it's slowly developing. So some examples of this would be new seepage areas, new seepage areas in or near the dam. So again, as the owner most familiar with this structure, perhaps your dam does leak. There's some areas, some seepage areas that historically are there, but you go out one day and you identify seepage coming from an area that, historically you never saw before. Again, that's, as the dam owner most familiar with the dam, you're in a position to hopefully be able to identify that. Similarly, if there's a new sinkhole, any sinkhole in the reservoir area or the embankment, hopefully there's not current ones there. Any sinkhole is potentially a serious problem. Visual movement or slippage of any of the embankment slopes. So now we get into maybe this shallow slope failure, or hopefully not a deep-seated one, or if there's a measurable earthquake felt or reported within 50 miles of the dam. All of these might trigger an emergency level 1. At that point, you may want to contact the dam safety, state dam safety officer if you have an engineer. If you have an engineer on staff or kind of on board, you might want to reach out to them first. Today's with the advent of cell phones, it's easy to take photos or videos of whatever is occurring out there that you can send to either the dam safety office or your engineer. Get them to take a look at it and see if in their opinion this is something serious enough that should trigger activation of the emergency action plan. Then stepping it up a little bit, this would be an emergency level 2. This is a potential dam failure situation. It's something that is rapidly developing. Some examples of this would be spillway flowing. So you've got a storm event, flow in your spillway, and you see active erosion or scour either at the toe of the spillway or down the spillway channel. You have a sinkhole that's rapidly enlarging, cracks in the embankment with seepage coming through it, earthquake resulting in visible damage to the dam or appurtenances. So these are things that are going on at the dam that certainly are unusual, and they're developing rapidly, meaning that there may be no way of reasonably slowing these things down or repairing them. Going back to that emergency level 1, these might be new things at the dam, but they might be able to be addressed with some emergency repairs. Again, those would most likely be something that would be directed by your engineer or the dam safety office. But there are events or incidents that are occurring that are slowly developing that could be addressed before they get worse. This level 2 is meant to be something that is rapidly developing that you can't reasonably stop or slow down. An example of a project out in North Dakota, Renwick Dam, back in 2013. perhaps maybe should have put this as an example under emergency level 1, not emergency level 2, but there was a rehab project already underway at the dam because it was already known and identified that the auxiliary spillway was subject to erosion. So it's an aerial view. Obviously, this is the dam right here. This large area here is the earth-lined or grass-lined emergency spillway. Construction had already started, so you can see construction staging area right here. So they knew about the weaknesses, if you will, of the emergency spillway, that it was erodible. The reservoir was full at this time, May 2013, due to snow melt. They had a forecast of a fairly significant rainfall, 4 to 6 inches were predicted. So in response to this, and like I said, this probably is a better example for emergency level 1 than rather than 2. But they were able to construct an emergency dike across this auxiliary spillway right here, raise the level of the auxiliary spillway to prevent flow through it. In addition to that, they did evacuate 1,300 people downstream as a precaution, but they were able to prevent the rainwater, the rising water in the reservoir from flowing through the auxiliary spillway, which would have likely certainly eroded and could have maybe led to a breaching failure. So this is an example, really. I apologize, I should probably had it under emergency level 1, where they identified a potential situation and were able to address it before it developed into an actual potential dam failure situation. Then emergency level 3 is really an urgent level type of problem, meaning that dam failure is likely or imminent or even in progress. So this examples would be, major overtopping flow eroding the embankment, damage to the dam or appurtenances that have resulted in uncontrolled release of the water, or earthquake that results in uncontrolled release of the reservoir water. So this is basically a failure is occurring. So again, as the dam owner, you're in the best position to make this initial determination or identify the problem, hopefully early on. If there's enough time to consult with dam safety or your engineer, and then if it's deemed to be a serious enough event or situation, like a level 2 or perhaps level 3, then obviously the EAP has to be activated. The people in the flow chart, notification flow chart, have to be contacted, and probably evacuations occurring downstream. Now, keep in mind that as the dam owner, we've mentioned what your responsibilities are, which include the preparation and upkeep of the EAP, this early detection, identification of a problem. Many of these problems evolve over time. So perhaps you catch it early, but it's still serious. You activate the EAP, you make all the contacts, but the situation may be progressing, maybe unfortunately, in the wrong direction, getting worse. So as the dam owner, you're also in a position to perhaps stay on site so long as it's still safe to do so, and communicate the changing conditions again to the emergency managers that are then responsible for dealing with things downstream. So that's where communication is important. And again, the responsibilities of the dam owner may fall to you to update people of the evolution of the problem. It may be getting worse. Perhaps if something that was caught early, you were able to do some kind of repair, it resolved the problem, and you're able to then perhaps go to a termination state. The important thing to know is that you are not responsible for evacuations downstream. You're not responsible for contacting anybody other than who's listed in the notification flow chart. So again, your responsibilities mainly are just at the dam. Issues about evacuations and dealing with people downstream, that goes to the emergency management officials, and they are experts in dealing with that. So we already touched on this, that after the emergency level has been terminated, after the level's been determined, the people in the notification flow chart for the appropriate emergency level shall be notified immediately. I kind of jumped ahead. So this is notification and communication that you're responsible for the different emergency levels. So for the emergency level 1, which is something that's developing slowly, you should contact dam safety or your professional engineer, get their input on it, and then a decision made whether the notification flow chart should be activated. For level 2 and also level 3, definitely the emergency notification flow chart should be activated, because these emergency levels can perhaps pretty quickly lead to a dam failure. So you don't want to waste any time. And then you want to keep in frequent contact with emergency management officials to keep them up to date on the condition of the dam. So this is what I was describing as far as the conditions, can be evolving, either getting worse or hopefully getting better. You want to make sure you keep everybody updated to that. This is an example of an emergency notification flow chart. So it all starts here with you as the owner, again, because you're in the position to identify these problems. Your first responsibility then would be to contact the immediate downstream emergency management officials. And it could be broken out as local emergency management people, highway patrol, police departments. There could be multiple downstream municipal entities, so you would be contacting them in order closest to the dam and then working further away. There may be some other technical reps, like maybe your own engineer that you would want to contact, as well as dam safety. So this is an example of a flow chart. There'd be actual names, phone numbers, and maybe emails listed for each person in this flow chart. And those are the names and phone numbers that would be checked and then updated annually if need be. This is just describes the contents of that notification flow chart, and why that's important to keep up to date, because those are the people that you're going to rely on in the event of an emergency. Some expected actions after emergency level has been determined, notifications have been made. The EAP should contain actions to be taken for each emergency level. Possible remedial actions should be included for several situations involved with emergency levels 1 and 2, if time permits. So again, those are the less serious levels. Perhaps you would be able to mobilize some construction equipment, materials, and basically, provide a repair that hopefully would stop the emergency. Immediate implementation of these remedial actions may delay, moderate, or even prevent the failure of the dam, and that's ideally what you're doing. So it's also a good idea to list some emergency contractors that are local to you or local to the dam, that have the manpower, equipment, and resources that they could respond quickly with manpower, equipment, materials to implement a repair. And the repair itself would be something that would likely be directed either by your engineer or the state dam safety office. The last step is termination. So when the EAP has been activated and the emergency is over, the event must be terminated and then follow-up procedures completed. The state dam safety official is responsible for terminating the operation and relaying the decision to the dam owner. There's some states where the termination is actually kind of a collective effort between the emergency managers, downstream emergency managers, dam safety officials. The emergency managers are the ones that understand the potential impacts, if you will, to the population that are downstream, whereas the dam safety officials, along with your engineer and the owner themselves, understand the dam and how it works and that sort of thing. So the actual decision for termination many times is sort of a collective effort. All persons notified during the activation of the EAP must again be contacted to let them know the event is over. And the dam safety emergency situation report shall be completed to document the emergency event. Not all states, not all EAPs have these emergency situation reports, but usually the emergency managers and oftentimes the dam safety folks do want to create kind of a record or document of what happened, ideally to identify what went well and maybe what didn't go so well. So if there's improvements that can be made to the EAP or the process itself, they can do that. So as far as the maintenance of the EAP, it should be reviewed annually, revised as needed, periodically tested, meaning that the exercise is performed. Again, in North Dakota, it's required every 5 years, and then maintain records of any revision dates and who the EAP is distributed to. And then there's a list of appendices that can be included in the EAP. Karen, I'm not sure, do you have a list of standard appendices that you require for your EAPs?
No, we don't. We just, what we have is just the recommended template that it's basically just the NRCS template that we recommend people follow as a starting point. We don't actually require that they use that if they have their own format that they want to use, or if they want to start with that and tweak it to fit their situation, we allow that as well. So we're basically just recommending that, and they can work with that to fit their situation.
Right. Okay. Well, this slide does present some ideas for things that might be included in the appendix based on the situation, the dam, the type of dam. So it would be left up to the owner how much of this stuff would be included. But certainly the inundation mapping is something that is included as part of the EAP. Oftentimes, just because they're fold out maps, they are contained in an appendix. So with that, that's the end of session 5. Do we have any questions? Are there any questions on any of that material? Okay. Session 6 is dam owner liability, public safety and security. We're now a little bit ahead of schedule. I was sort of rushing because I thought I was behind, but actually we're looking at having a break at 2:30. So why don't we take our break right now? A 15-minute break. So it's roughly 2:20 your time, Central Time. So let's convene back at 2:35, and I'll get started on session 6 then at that time. Thank you. Our last 2 sessions. First of all, can you guys hear me? And do you see session 6 on the screen?
Yep.
Okay, thank you. I see in the comments that Anna has posted a few other links to YouTube videos about site or public safety relative to dams. Apparently going down spillways. I didn't open any of these up, but I certainly know that that's dams and spillways in particular can be an attractive nuisance for adventuresome people, but they're very, very dangerous. And that's one of the responsibilities of a dam owner is that you can't prevent people from doing stupid things, but you need to do everything within your power to educate them on what the consequences may be. And that's essentially what we're going to be covering in this next session, session 6, on dam owner liability, public safety, and security. Let me start out by saying that I'm an engineer, not an attorney. The first part of this session that deals with the public, or with, I'm sorry, that deals with dam owner liability was actually put together by a practicing attorney for ASDSO and for these types of sessions dealing with that topic. So I will go through it. I'll be happy to try to answer any questions that anybody might have, but as I said, I'm not an attorney, and this is dealing basically with the legal side of the liability issue. So with that said, we'll be covering basic legal premise of dam safety and dam owner negligence. We'll describe or define what standard of duty is, and then once we understand that, the dam owner defense, and then we will then get into public safety liability and dam security issues. So learning objectives include identifying what dam owners' responsibilities are, the definition of standard duty, definition of strict liability, identify public safety responsibilities, and then identify dam security procedures. As far as basic legal premise, we live in a litigious society. I think most of us probably are aware of that. Widespread litigation will result from a dam failure, particularly a catastrophic dam failure, and everyone remotely associated with the dam will be sued. Those likely to be sued will include certainly the dam owner, dam operator, inspectors, engineers involved in either the design of the dam originally or any modifications, or engineers involved in the inspection and upkeep of the dam, contractors, state dam safety officials, and anyone else in the proximity of the dam at the time of failure. Lawsuits will claim extensive liability on the part of everyone involved in that dam failure incident. Now, negligence. The definition of negligence is the failure to exercise reasonable care to avoid failure of the dam under the particular circumstances causing the failure. For high hazard dams, there is a higher standard of care expected of the dam owner because of the resulting increase in risk downstream. Negligence can exist in any of the following aspects of a dam project: in the design, in the in the design, in the operation, in the inspection, any remedial dam repairs or alterations, construction, maintenance, or the regulation. Standard of duty: dam owners are considered responsible for carrying out the following duties: inspect the dam on a regular basis and completely inspect it, monitor conditions regularly, maintain the facility, and meet appropriate regulations and standards of care. They're also required to prepare and follow the operations manual, prepare, test, and update an emergency action plan, and also maintain a complete set of records. So several sessions ago, when we were talking about just general operation requirements, talked about developing standard forms that can document pretty much anything that you do at the dam, including inspections, any standard operations, exercising of gates, any maintenance activities. Having a complete set of documents that document those activities at the dam will certainly help you as a dam owner in the unlikely or unfortunate event of a dam failure. The minimum standards of duty are set forth in various areas and statutes and ordinances and regulations and in professional or industry standards. The breach of standard duty occurs when the dam owner does not maintain the standard of duty. And this breach of standard duty can be established through expert testimony, circumstantial evidence, common sense, and legal theory. Causation and damages. The breach of standard duty must be established as the causation of damage or injury to the plaintiff. Hello? Someone have a question? Damages associated with the dam failure often include loss of life, personal injury, emotional distress, and property damage, either as diminished value or the restoration cost or replacement cost of that damaged property. Public safety. Liability related to public safety. A dam owner or operator may be liable if there is a failure to warn or guard the public against injury from a dangerous condition that was known or should have been known. A dam owner or operator may be liable if there's a failure to properly construct or maintain in good repair any structure or recreational facility, or failure to properly control potentially hazardous recreational activities. Gross negligence of an employee is probable cause of injury. So this goes to say some of these videos of people going down spillways. Certainly it's impossible to completely prevent activities. It's not reasonable to have guards on duty out there 24 hours a day, 7 days a week to prevent people from doing stupid things. But it is the responsibility of the owner to warn or guard the public against injury from doing these dangerous acts out there. My voice is starting to get scratchy just from talking so much. Liability also related to public safety. The owner operator must identify any unreasonably dangerous condition and either correct the condition or warn potential victims of the existence of the condition within a reasonable period. The owner operator does not have to insure against possibility of injury, but they must act reasonably to prevent possibility of injury. So again, you don't have to absolutely find a way to prevent it, but you need to identify dangerous conditions and warn potential victims of those dangerous conditions. Courts often recognize that participants are sometimes injured in recreational activities. There's not always a person or agency at fault. Owners and operators are obligated to inspect all facilities and adjoining areas to identify potential hazards to the public and to take action to minimize risks of injuries. Owners, operators bear an even greater responsibility for the safety of children. This is because children are generally unable to understand the danger of certain conditions that a dam may pose. And as an example, signs alone may not adequately warn a child, and security fencing may be necessary. So if the sign is say difficult to read or just above the level of a child to understand what the danger is, then additional steps such as fencing might be required to reasonably prevent access to the dangerous area. For liability to exist, it must be shown that first an injury occurred, that a dangerous condition existed and had potential for harm, that negligent or wrongful actions created the condition, and the operator owner had knowledge of that condition. The dam owner operator must then make and keep the premises safe, avoid conduct or conditions that could injure any persons, even trespassers, correct existing dangerous conditions, and post warnings. Inspections for public safety hazards must be conducted at frequent intervals, conducted at times when normal conditions are likely to have changed, such as following heavy public visitations, floods, storms, that sort of thing. And then the owner should document whatever the proposed corrective actions are. Remedial actions when completed must be documented. If any accidents occur, they should be documented, and then accidents must be followed by immediate corrective action. Common hazards associated with dams include spillways, stilling basins. Those are the areas at the downstream end of the spillway or the outlet pipe, the outlet works or intake structures. So any of the spillways or structures associated with the spillway out in the reservoir, power intake channels or open channel conveyance structures. Other hazardous areas around dams include walls, cliffs, and steep slopes, power lines, certainly if it's a hydroelectric facility, and swimming beaches. Public safety precautions, use signs to direct, inform, identify, inform, or warn the public. The sign should be located to gain visitors' attention, and they should convey the nature of the hazard posed by specific conduct. The sign should also warn of the hazard with intensity commensurate with the potential outcome, explain how to act to avoid injury, explain consequences of failing to obey, which sounds like an awful lot to convey in a single sign. But this is an example of one that does a pretty good job. Obviously, large letter font, red background, danger, certainly should get most people's attention. Saying what not to do, so no swimming, reason why, turbulent water, and dangerous undertow, and what they should do is stay out to stay alive. Public safety precautions, some examples of this. The most common protective device is fencing to restrict access to hazardous areas, although this particular photograph is really showing railing instead of fencing, but some judgment can be applied whether railing by itself or actual fencing should be used to isolate or protect a specific dangerous or area or hazard. Here is an example of an intake tower or reservoir. You can see the degree of fencing along the entire walkway out to the tower. The closest area of the walkway to the embankment has an even higher fence section, and it's also got a warning sign. Again, the sign does a pretty good job, very large font, orange background is warning. It's like this, similar to the previous sign that had danger. It's telling the passerby that hazardous conditions exist, not what to do. So no swimming, no boating, no fishing, and basically just no trespassing. This happens to be a privately owned water company dam. So the entire site is fenced. Perimeter of the reservoir is fenced, but then additional precautions made here at that intake tower. So different types of precautions, guide rails, guardrails, or bollards can be used to restrict vehicular access. Floating barriers can be strung out across the reservoir upstream of the spillway areas or intake areas to restrict or delineate recreational users and provide a means for self-rescue so that they don't get too close to the hazard area of the spillway or the intake. Safety ladders can be installed as a means of escape from steep slopes, walls, open channels. Public awareness program. Again, if it's if public access is encouraged, but safety is a concern, then brochures, videotapes, and websites can be developed to educate possible users of some of the dangers associated with the site. Some examples, again, fencing around an outlet structure. Here, obviously, they can gain access to it, but the fencing is put up and around it to prevent someone from falling down into the outlet structure, given the height of that fall. And if this were actually flowing, if the outlet pipe were flowing, you could have some turbulent water in that structure as well that could present a danger. Here is some railing around a drop box spillway. And a danger sign. So again, this is meant for presumably recreational users of that lake. If they get too close to that spillway, they at least have the ability to grab onto that railing and hopefully pull themselves to safety. Showed this photo earlier of the floating barriers around that overflow spillway. This is a recreational lake. There is a boat launch there in the upper part of the photograph. So you do get small boats, kayaks, canoes using this particular lake quite a bit. So there's a series of buoys around the spillway that have signs on them, essentially alerting them to the danger of the spillway. Are there any questions on any of that liability and public safety at dams? Okay, next section is dam security. This was developed essentially in response to the events of 9/11. A lot of the owners that we deal with are larger owners that have the reservoirs for public water supply or power generation, and are potential targets for like terrorist or vandalism types of attacks. So there's an awful lot of detailed information here relative to dam security. There's a number of governmental groups put together and committees to deal with this through the dam sector, as well as other power generation sector and other sectors, infrastructure sectors across the country. I know that a lot of the dam owners that attend these owner workshops, this is not an overriding concern. So I'm going to go through this. All this information is obviously there for you to review in the overall presentation that Jennifer's made available for you. But I'm going to guess that this may not be of super high importance to a lot of the owners attending. So I will go through it, but kind of quickly. So why is dam security important? We're going to cover all this quickly in here, talk about security awareness, talk about threats, vulnerabilities, and consequences, protective measures, such as controlling access, deterring and detecting intrusions, protect against explosives, and reducing consequences. Talk about crisis management, mainly having plans in place and exercises so people are prepared with pre-planned responses to these things, and then access to additional resources. For the presentation that we're giving right here, we got a lot of the information from these three documents. These documents can be obtained through Homeland Security Information Network, the Critical Infrastructure Dams portal, but most of the information provided here basically comes from these three documents. Why is dam security important? The degree of protection for a dam against damage or loss caused by intentional acts. The dam projects may be attractive targets because they are essential physical structures that deliver project benefits, often with public access. Understanding the risks facing the organization can help make decisions to manage those risks to an acceptable level. Integrate security into dam safety programs. This helps to protect communities upstream and downstream from risk, regardless of the cause. Ensures reliable and dependable delivery of project benefits by securing and protecting facility assets and operations. So this goes to the owners that are, have dams and reservoirs for, say, water supply, power generation. They take the responsibility of stewardship of those assets very, very seriously. So it is important to them to ensure the reliability and dependability of the project benefits, and also to prevent the life safety incident from becoming a security incident. How do dam safety and dam security relate? Well, in risk from a dam safety point of view, risk is a product of the likelihood of a structure being loaded, adverse structural performance, and the magnitude of the resulting consequence. Does not consider physical or cyber security risk. So that's the dam safety stuff that we've been talking about up to this point. So the likelihood of the dam being loaded to the point of failure from some natural event, adverse structural performance, and then estimating the magnitude of the resulting consequence. Risk associated with security comes from the potential for an unwanted outcome resulting from an incident, event, or occurrence as determined by its likelihood and the associated consequence. Those seem like just a lot of words to me, but essentially it's not so much natural events, but man-made events that are trying to produce a required outcome, such as perhaps a dam failure, dam breach, or maybe just loss of use of the reservoir. Why target a dam? Because adversaries select targets to meet a motive, exploit vulnerabilities, and deliver intended consequences. Understanding why an adversary selects a target and how a threat might be carried out can help to identify suspicious activities and indicators of possible threats, and also to take action to mitigate a vulnerability and or enhance protective and security measures. So again, dams do represent large components of our nation's infrastructure. So it is oftentimes just the optics of being able to damage a dam that would give the perpetrator of this the results that they're looking for. Sorry. So potential security threats, the adversaries and the types of attacks. A threat, any natural or human caused occurrence, individual entity or action that has or indicates the potential to harm life, information, operations, the environment, and or property. The types of adversaries could be terrorist organizations, cyber threat actors, insiders, or just criminals. The types of attacks could be an armed attack, chemical, biological, radioactive material attack, cyber attacks, the use of explosives, unmanned aircraft systems, or attacks on vehicular or mechanical equipment. The sources of this potential threat information comes from a variety of places. It could be from expert knowledge about past or potential future threats or hazards, existing assessments conducted by the organization that the organization responsible for the dam, records from previous incidents, including historical data, forecasts or models of future risks due to changing weather or demographic patterns, input from local law enforcement and or emergency management agency, information or intelligence from a state or local fusion center, or national threat alert or bulletins such as those issued by the Department of Homeland Security or the FBI. Indicators of a possible attack, and this is not meant to be an all-inclusive list, might be the identification of loitering, parking, or standing in the same area over multiple days with no reasonable explanation, the unexplained use of binoculars, cameras, and recording devices, persons not associated with the dam asking technical questions, theft of uniforms, identification cards, and or access credentials, missing safety equipment or other items out of place, delivery of suspicious emails, repeated attempts from the same location to access protected computer information systems, employees, customers, suppliers, or partners unable to access the organization's systems or website, anomalies really of any kind in the control system, behavior, or alarming. Certainly it's important to report any type of suspicious activity. So it's important to maintain awareness of the environment of the dam and the surrounding area, identify behaviors that are out of the ordinary. And if those are identified, the activity should be reported with as much detail as possible to any number of those possibilities, but probably most importantly would be to local law enforcement, and then they can elevate it if they feel it's necessary. Potential security vulnerabilities. Again, not an all-inclusive list, but any physical feature or operational attribute that renders an entity, asset, system, network, or geographic area open to exploitation or susceptible to a given hazard. So site-specific vulnerabilities would arise from specific policies, procedures, systems, or designs of a particular site. If there's dependency, reliance on the functioning of another site or infrastructure, and or interdependency, the relationship between two or more sites or assets by which the condition or functionality of each is affected by the condition or functionality of the other. Specifically, areas of vulnerabilities for dams, pretty much any of the mechanical systems on dams are relatively easy to damage compared to, say, the mass structure of an earth embankment dam or a concrete gravity spillway. So crest gates are a potential area of vulnerability. Hydroelectric facilities where you have intake piping, penstocks, electrical controllers, just a lot of pertinent systems and facilities associated with the dam that again are relatively easy to damage compared to the mass of the dam itself. Instrumentation in a dam, again, is a potential vulnerability. If you have a piezometer that extends vertically down into the mass of the embankment or the foundation, or you've got some kind of internal drainage system with an outlet pipe that, again, if you go up, that pipe extends into the base of the dam, those would be areas where perhaps explosive charges might want to be set that could do some damage to a mass structure like an earth embankment dam. Conduits and inlet outlet structures, also when there's water not flowing through them, they can provide access up under the dam. So it'd be an area where explosive charges could be set and do some real damage to, if not just the outlet pipe or outlet structure, the dam structure itself. Vulnerability assessments are conducted, and there's a certain process for this where you identify and group assets and vulnerabilities using common threat scenarios, consider vulnerabilities associated with physical, cyber, and human elements, the physical being spillways, intake structures, outlet works. Cyber might be control systems or business systems, and human elements would be personnel. on-site personnel, including contractors or outside people that come onto the site, identify dependencies and interdependencies with other assets, analyze existing protective programs and securities, and assess residual gaps to determine unresolved vulnerabilities. Existing assessments are conducted by the organization, procedural and programmatic gap analysis, exercise, observation, and after action reports. These are the different sources, inspection programs, and input from local law enforcement. These would be the sources of identifying areas of vulnerability. Once vulnerabilities are assessed, then you need to assign consequences to them. So that consequence is the effect of an event, incident, or occurrence with an estimation that reflects the level, duration, and nature of the predicted loss. So failure of the dam would be a loss of capability to impound water, damage or destruction of sector assets, including appurtenant structures and personnel to operate and secure the facility, disruption in service, loss in the project's ability to operate as intended, human impacts. These are all consequences that could come from some of these vulnerabilities. Human impacts would be the effect on human life and physical well-being, economic impact, property damage, loss of area businesses, repair or replacement of costs, emergency response, cleanup costs. Impacts on the mission functions, damage or disruption to water supply, irrigation, hydropower, navigation, flood control, or recreation. So whatever the mission of the dam, the purpose of the dam is, the impacts would be the disruption of those missions. Certainly a national level impact could impact national security, total economic costs, and public confidence. And that might be the most important thing, where the public really does expect us to protect these infrastructure assets. And it's a level of expectation now. There's a number of resources for the consequence estimation. These again can be accessed through Homeland Security Critical Infrastructure Dams portal. If you're interested in this particular topic, taking action during heightened threat. Take actions now to address security vulnerabilities and or identify enhanced protocols and measures to implement during times of heightened threat. Sources of threat information would be come from the Department of Homeland Security National Terrorism Advisory System that issues bulletins and alerts. There's state emergency conditions, state EAP requirements, and then state and federal regulatory requirements. There's the strategies to reduce risk. What response procedures should be followed to reduce the risk if the threat condition is elevated or an attack occurs. You should review response actions annually, exercise the emergency action plan and other plans as applicable, and revise as necessary. So although much of this may be beyond a normal dam owner, let's say, certainly within your capability, and it is a requirement of the state, is the development of an emergency action plan, exercising it on a regular basis, as well as updating it on a regular basis. And all of those things, all that attention to the emergency action plan will reduce risk associated with the dam failure, whatever the cause is. Implement enhanced security protocols that could take any number of any number of forms is listed there. If the dam is at a remote location, implement protective measures to heighten security. Review all critical information about the dam that is currently available to the public and determine what information should be removed. And then protect access to information about critical and vulnerable parts of the dam. I know here in New Jersey, because of our location, there following 9/11, they did go through and identify a number of dams that were considered critical infrastructure. They did have these vulnerability assessments performed on the dams. Prior to that, there was a system where inundation maps were available to the public, but it was deemed, possible security risk to have that information available for initially for all of the dams, and then ultimately just for those critical dams. So that information then was pulled away from the public and no longer made public. So this has resulted in actions being taken, certainly here in New Jersey. Controlling access. Again, this is something that is a little bit more tangible and might make sense as far as controlling both physical and access to cyber assets, active and passive vehicle barriers, vehicle ramming considerations, waterside barriers, perimeter fencing, analog access control, taking the form of locks. It's serious terminology for locks, electronic access control to physical assets, and then cyber controls. So the photographs show vehicle barriers in the upper one, and then waterside barriers across a reservoir that could all be used to control physical access to the facility. A little less intense would be just fencing around the perimeter of the dam, access gates at access points, as well as additional fencing to, say, intake towers and some more critical elements of the dam. Ideally, you want to deter and detect intrusions. So both physical and cyber assets, security fence or security force can be used to deter or detect intrusion. The use of canines, closed circuit television, sensors, lighting, and intrusion detection tools. There's a number of procedures to protect against explosives, standoff distance and facility hardening. Explosives are a favorite tactic of terrorists. Amount of damage depends on the construction of the targeted asset, type and quantity of explosives used, and where the device is placed. So this gets into, say, some of the access points, instrumentation or outlet pipes that can give you, gain access to the central part of a dam or the foundation of a dam, or if a large enough explosive force was used, could seriously damage the dam. Certainly the mechanical elements of the dam, gates, spillway gates, or hydroelectric elements on a hydroelectric dam, require a lot less explosive force to damage those kinds of things. So some of the protection strategies include this idea of standoff distance and facility hardening, and then consider trade-offs when making decisions. To reduce the consequences, you want to be able to respond and then recover quickly from an incident. So you want to implement your emergency action plan to minimize the life safety consequences caused by damage or failure of the dam. So ideally, you want to limit the progression of initial damage or cascading effects. You want to be able to guide evacuations. Again, that's the responsibility of the emergency managers. You want a reference list of tools, equipment, and stockpiled material, as well as a list of contact lists for contractors and vendors that can be used to mobilize and construct repairs if possible. Use engineering, construction, and operational measures to prevent initial damage from progressing and causing catastrophic damage, and then reestablish the dam's function after successful attack as quickly as possible. Crisis management, the ability for an organization to manage incidents that have the potential to cause significant impact, enhance resilience by guiding emergency response and helping operators rapidly restore partial or full operations while effectively communicating about the crisis and maintaining operations throughout the process. This includes plans to guide emergency response, crisis communication, rapid restoration, and continuity of operations. It also includes exercises to validate and update these plans, test communication protocols, and clarify rules and responsibilities. So although this is really talking about a higher level of security, if you boil this all down, this is essentially what your emergency action plan is intended to do for these dam safety incidents that we presented in the last session. So different types of plans that can be developed. Certainly probably for most of our use of the emergency action plan is the most important one. But as you get a little bit more sophisticated when it comes to security, there could be a hazard specific response plan, crisis communication plans, recovery plans, continuity plans. Again, for the vast majority of dam owners, it's really just the EAP that is required. But as you get into more sophisticated owners of these larger dams that provide critical infrastructure, then these other plans really become important to them. Conducting exercises is critical, and for the same reasons that we talk about it with the EAP. I won't go through all of those, but again, exercise helps familiarize people with the contents of the specific plan. It allows you to go through it in a non-stressful situation, and hopefully identify if there's any gaps in the plan during a period where it's not critical that the plan works. And the idea is to get the plan in shape so that when there is a real incident, when stress levels are high, that the plan works well. So Homeland Security Information Network, this critical infrastructure dams portal, is a place where DHS and critical infrastructure stakeholders communicate, coordinate, and share information. It provides web-based tools to enable information sharing within that sector. This tells you how to access the dams portal. You have to basically request access, and then you'll be sent information for it. Some of the resources there's some fact sheets, physical security publications, cybersecurity publications, as well as other information. That's it for liability, site safety, and security. It's a relatively dry session. I hope I didn't put too many of you to sleep. So any questions at all on any of that? Okay. We're going to move on to the last session, session 7. Repair projects, hiring an engineer and consultant, costs and funding options. Are you seeing that screen, everyone?
No, not yet.
You're not seeing it?
No.
I don't know what's happening here. Every time I change, I must lose that ability. So.
There it is.
All right, good. At least one person's awake out there, right? Okay. Repair projects, hiring an engineer, consultant, costs, and funding options. We're going to talk about the rehabilitation process, some steps in hiring a consulting engineer. Once again, the dam safety website that does contain a lot of this information for dam owners. We're going to talk about 4 different categories of dams, come up with typical dam repair costs for those 4 categories. We're going to talk through a couple of case studies. which will describe the elements of various dam repair projects or techniques, and then finish the session with some funding opportunities. Excuse me. As far as learning objectives, we hope you'll be able to learn how to retain a qualified professional engineer for the repair or the inspection of your dam, identify some typical dam repair costs, and then identify potential federal, state, and local funding sources. The process for getting the job done. This is selecting an engineering consultant. Ideally, you want to meet with potential consultants to receive proposals. Generally, it's recommended that you try to get 3 proposals. Are you not seeing this now, or are you seeing this?
We can see it.
You can say, okay. I'm just looking at a text from Jennifer. It said no slides. Then once you've met with the 3 consultants and received proposals, you want to pick one of the consultants and enter into agreement with them. The consultant begins the design process, generally with either he doing it or having a sub-consultant do a surveying of the dam, perhaps some geotechnical investigations. Those would be either some holes drilled vertically through the dam and into the foundation, or maybe just some test pits excavated. The idea is that you want to see what the soils are that make up the dam and the foundation, and see what kind of state they're in, how well they're compacted, that sort of thing. From those geotechnical investigations, you can send those samples then to a laboratory to have certain lab tests done that will classify those soils, that will help you then estimate the seepage potential through the dam, also the strength of the soils, and some other characteristic types of tests for the soils. Then once all that's done, the engineer would go into developing preliminary plans, a review of those plans, and then into developing a final set of plans. Once the plans are completed, then they would go into permitting phase, where the plans are typically submitted to at least the state dam safety office for review and permit. And then there may be some other state agencies, and in certain cases, some perhaps federal agencies, maybe the Corps of Engineers would take a look at the plans, but typically it would just be local and state agencies that review it. While the permitting is being done, the consultant can then reach out to a number of construction firms to get bids on the construction of the work. Again, recommend a minimum of 3 bids. Based on those bids, the owner would then hire the contractor with recommendation from the consultant, and then proceed into construction. This is a very rough bar chart schedule of just sort of order of magnitude timeframes. I guess, it's going to vary very much on how big and complex the dam is, and how extensive the rehabilitation work is. But in general terms, usually the design part will take upwards of about a year to complete. Permitting may take several months after the design is completed. So the design being essentially those first 4 rows, hiring the consultant, surveying geotech, and then developing the construction drawings. That can take upwards of a year. Could be more if it is a more complex, larger dam. Then permitting. This is showing an overlap here, which implies that the engineer should be in communication with the dam safety office during the design phase. Let the state dam safety folks know basically what the problems are, what the proposed solutions are. But ultimately, there'd be a permit package submitted, formally submitted at the end of design, at which the state agency would then review and approve. That could take anywhere from a couple months to maybe longer than that. Hiring a contractor should only take a matter of maybe a month or so. And then you would start construction. This particular schedule was truncated. Construction, again, the duration of construction very much depends on how extensive the rehab is, how complicated it is, but it could be anywhere from 3 to 4 months to 12 to 15 months to 24 months maybe. So it can extend quite a period depending. As far as retaining the professional engineer, there is a fact sheet that's available on the ASDSO website that gives some details and some guidance on the best way to retain a professional engineer. Some of that information is summarized here. So the need for retaining professional engineer, these would be some of the deficiencies at the dam that would require an engineer's involvement. Certainly any type of spillway problem, inadequate spillway or storage capacity, severe spillway deterioration. If you have embankment slope failures or problems, extensive seepage or sinkholes, all of those things would require a professional engineer, as would large cracks in the embankment, severe erosion of the upstream slope, inadequate or lack of outlet erosion control structure, so that it could either be no energy dissipating device at the outlet end or an improper one, so you have a lot of erosion or scour at the outlet end of your spillway, and no lake drain or low level outlet. So the repair or replacement of these things would all require an experienced professional engineer. How to find a qualified engineer? You could certainly start with your dam safety program. Generally, they're not going to be able to recommend a single firm, but they could certainly tell you or give you a list of firms that do practice in the state. You could certainly ask them some questions as well, as far as what firms do they see most often submitting repair permits, rehabilitation permits. What firms do they have the best luck with, let's say, the fewest comments on their designs, that kind of thing. So it can help you sort of whittle the list down to maybe a handful of firms that do a lot of work in the state. You could also contact the State Board of Registration for professional engineers. There's also a state consulting engineer council that you could contact. However, that is a group of consulting engineers. So if you contact them, they're probably all going to say they can do this kind of work. Referring to a local telephone directory or doing a web search. I'm not sure. Honestly, that's listed here, but I don't know what kind of luck you would have there. And then talking to other dam owners, certainly other dam owners that have gone through the rehab process, they certainly should be able to give you either a positive or negative recommendation on who they used. But I think between that and contacting your state dam safety program are your best ways of at least identifying a number of qualified engineers. The types of qualities that you want to look for would be companies that have a strong background in civil, agricultural, geotechnical, or water resource engineering. Certainly the state should be familiar with the state dam safety laws and rules, which means that ideally the engineering firm is located in the state, but they don't necessarily have to be if they're in an adjacent state, but maybe do a lot of work in your state, and certainly could be familiar with the state rules and regs that way. And they should be able to show you a list of experience, recent experience of showing projects that have design of dams and hydraulic structures. And most engineering firms are happy to show that kind of experience.
So the types of company specialties, you're looking for disciplines of hydrology, hydraulics, geotechnical engineering, and even structural engineering for the concrete elements of a dam. The company should be willing to provide a list of dams that they've worked on, and the company must employ engineers that are registered in the state in which the dam is located. So most dam safety regs will say that a design, a rehabilitation design must be performed under the control of a licensed engineer or an engineer licensed in that particular state. So here we're just going to talk about a couple of examples of sort of a kind of quote unquote typical dam repair or rehabilitation project. We're going to go through some of the various repair activities, construction activities that will be required to give you sort of a sense of the scope of these things and the different things that are required in rehabilitating different types of dams. So in this example, we're going to be talking about a spillway replacement for a 22-foot high earth embankment dam. This group 2 basically refers to some groupings that we're going to talk about a little bit later, where ASDSO put together a committee to develop what the overall cost to rehabilitate all of the dams in the U.S. that require rehabilitation. So that committee, took on that task. I'm going to present some of their findings at the very end here, but they essentially broke all of the dams in the United States, and there's over 90,000 of them, into 4 categories, basically just based on height. So I'll define what those different categories or groups are, but a dam that is 22 feet high would fall into group 2 of that breakdown. So for this particular example, we're going to replace the spillway, raise the embankment 6 feet in elevation, and replace the lake drain. So some of the elements of work that would be required. This is, the construction activities that would be required. Be flow diversion. The spillway is the element of the dam that does pass your base flows and any storm flow. So if your project involves the replacement of the actual spillway itself, the question is, how do you then pass flows through the reservoir? Even if you're able to completely empty the reservoir, if the construction takes 6 or 12 or 24 months, more than likely you're going to have several rain events, storm events during that period of time that's going to produce runoff that's going to flow down into that reservoir, and you have to have a way of being able to divert that flow around the spillway reconstruction. So I'll show you one example of how that flow gets diverted. Once the flow is diverted, you've now isolated that spillway that needs to be replaced, so you can go in and demolish and remove that existing spillway structure. In this particular example, there is a new spillway that's constructed using cast in place concrete for the new spillway. There's a new concrete outlet channel and stilling basin that are constructed, as well as an under drain system, a drain under the spillway. We're also going to be replacing the existing lake drain with a new lake drain consisting of a gate and outlet conduit. We're going to provide additional earth fill, topsoil and seed on the embankment to raise the crest. We'll provide some riprap and drainage material on the upstream slope of the existing dam, as well as the raised section, to prevent any erosion of that upstream slope. The types of professional services that would be required would be surveying and subsurface investigations, design engineering and permitting, and then oversight by an engineer during the construction phase of the work. So here's just some photos illustrating a project that closely matches this example. This is a view of the existing dam and reservoir before construction. We're looking at the dam from the right abutment. If you recall the orientation, this is the right abutment. This is the earth dam extending along here. There is some existing stone and riprap on the upstream slope, although it's pretty small, and there's some vegetation clearly growing up through it. It's hard to see in this photo, but the existing spillway is right here. It's basically a concrete box culvert that extends through the earth embankment. It does support an access road along the crest, and there were timber stop logs along the upstream face of that culvert that controlled flow through the outlet culvert. Over here, adjacent to this right abutment, is a gated outlet pipe. This site was quite old, and there used to be a mill located on this right abutment. So this gated pipe used to be a gate and sluiceway that fed water to the mill that milled grain at the time. So this spillway is quite small, quite inadequate. Also in very poor condition. The concrete is failing, actually. Again, it's hard to tell from this photograph, but it is only about 8 feet wide. That's important because when you see the construction and the size of the new spillway, it will give you an indication how completely undersized this current spillway is. So the idea was to isolate this spillway so it could be removed and the new spillway constructed within the roughly the same location, but we had to divert the stream flow and any storm flow. So this gate and pipe through the embankment here at the right abutment basically was used as a diversion system to divert flow through. So one of the first steps the contractor did was install a sheet pile cofferdam out in the reservoir. Sorry. So this is actually an aerial view. This is the existing spillway. You can see it a little bit better. There are 2 sets of these timber stop logs that are pulled up with this. Actually, they were timber gates. So basically timber planks were connected together. So there were timber gates that are pulled up by these operator mechanisms. Each one, I think, was 4 feet, maybe 5 feet wide at the most. So this overall dimension here is anywhere from 8 to 10 to 12 feet wide. This was the access road across the crest of the dam. So to isolate the spillway so we could demolish that existing spillway and then construct the new spillway, this steel cofferdam was placed out in the reservoir, which allowed then all the flow to be diverted through that gate and valve that are towards the right abutment, which are just outside the view of that photo. Here is pretty much the same timing. Here is the cofferdam up in the reservoir, isolating the existing spillway for demolition and gives us room for construction of the new spillway. We also have a downstream cofferdam because there's a fairly large pond on the downstream side. We didn't want this water to flow back into our construction and excavation site. And again, the water is being diverted just below the limits of this photograph through that diversion pipe. Here, the project's progressed. The existing spillway has been demolished and removed. A portion of the embankment has been removed. This shows that diversion area. So this is the gate and pipe towards the right abutment. Here is the right abutment. The structure was the old mill, it's still there. So all of the stream flow right now is being diverted through this area over here. The spillway area is totally isolated by the cofferdam. So the existing spillway and embankment section have been removed. Right now, foundation piles are being installed for the new spillway. This is the new spillway being constructed, now looking towards the upstream side. So this is the reservoir. This is the right abutment over here. This is the diversion channel going through that pipe. Cofferdam is still in place, upstream and downstream cofferdam. So new spillway walls. This is a new low-level outlet right here. There's a gate being installed right here. So the water can flow through this channel, through this gate, and be discharged into the stilling basin. A new semicircular OG-shaped weir. And this does give you some kind of scale of this new spillway. This is, a conventional transit mix truck for the concrete. This is a pump truck. So this is obviously quite a bit larger than the twin 4 or 5 foot wide timber gates that were here before. Owner still wanted access across the crest of the dam. So precast box culverts are installed. So flow will go over this spillway section. There'll be a concrete channel constructed into, to conduct flow through these precast box culverts into this riprap stilling basin and then into the downstream channel. Here, the spillway is completed and the embankment is being raised. So this is the completed OG spillway with flow over it. This is the channel for the low-level outlet. There's a gate right there. You can see the water, going over the spillway through this channel, through these twin culverts, and it's being discharged now into that downstream channel. And they're in the process of raising the embankment. A second example for a typical repair project would be providing overtopping protection. Again, this would be a dam that would be classified in that group 2. It's only 20 feet high embankment dam. Same problem as the previous project. It's the spillway is inadequate. However, the previous project, not only was the existing spillway inadequate, but it was also in very, very poor condition. It was failing, so that's why the decision was made to demolish it and replace it with a new spillway system. This particular example, rather than demolishing and replacing or enlarging the spillway, the decision was made to provide overtopping protection. This is where an armoring material of some kind is placed over the crest and downstream slope of the embankment to armor the embankment. So if a storm occurs that produces discharge larger than what the spillway can handle, then the reservoir will rise up and flow over the armored section of the embankment, and the armoring then prevents any type of erosion. So it does allow the overtopping. Different elements of work that would be required. Certainly the topsoil would have to be stripped from the crest and downstream slope. Whether the dam is currently leaking or not, it's a good idea to place drain material on the downstream slope so that drain material basically would go underneath the armoring material. That way, if the dam is currently leaking or if a leak starts to occur sometime in the future, there's already a drain in place to pick it up and safely conduct the seepage to the downstream toe. Following that would be the placement of the overtopping armoring material. And there are a number of different materials that can be used to provide that overtopping protection. Roller compacted concrete, articulated concrete blocks, cast in place concrete, and gabions. And I'll show examples of each of those and describe them a little bit in more detail. Here's just some limitations associated with each of these. RCC. The advantage is that it produces the most robust overtopping protection of these four materials. So it can withstand almost unlimited depth of overtopping and duration of overtopping. But one of the limitations is that it's usually produced on site, and therefore it requires a relatively large staging area on site for the on-site plant that would produce the RCC, as well as the materials that go into making it. Articulated concrete blocks are precast blocks that are cabled together to form a mattress, and I'll show you some examples of that in a minute. Some limitations there are that they've been tested in laboratory, full-scale laboratory tests, and they're stable for flow depths of up to 4 feet. So if the analysis by your engineer shows that the overtopping depth is greater than 4 feet, then articulated concrete blocks, or ACBs, probably are not appropriate. You would have to go to RCC, the roller compacted concrete. But for depths of overtopping less than 4 feet, the ACBs work quite well. They come to the site prefabricated into these mattresses, so they are placed just with a crane. So there's a smaller staging storage area required than compared to the roller compacted concrete. Conventional cast in place concrete would likely have to be reinforced. It can be used if it's a relatively small application, small dimensions. If you get into larger dams where you have larger surface area, the cost becomes prohibitive compared to the ACBs or the RCC. It's also difficult to get it to placed on the slope that most embankments have. On the downstream slope, a 2 horizontal to 1 vertical slope. When you go to consolidate the concrete with vibrators, it tends to want to run down that slope. And attention has to be paid to both the design and the proper construction of the joints. Because it's conventional concrete, it will be subject to cracking. You want to try to control that cracking with joints, but you want to make sure the joint details are such that they can withstand the overtopping flows without erosion. And then lastly, gabions, which are rock-filled baskets. They've been used in some applications. Again, they are limited as far as their stability to depths of overtopping, usually 4 feet or less. However, they are subject to vandalism because they're in these wire baskets. If the public can get to them, the baskets can be cut or just unraveled, which then they lose their confining capability, and they're also subject to corrosion. The baskets are steel, and they can either be galvanized or PVC coated, but both of those, obviously when they're being filled with the rocks, can be nicked, and then you can get corrosion at those points. So long term, the baskets can fall apart. There's a question in the comment section about what overtopping material will be recommended for North Dakota extreme temperature variations and freeze thaw, which is a very good question. The ACBs, and I'll show you a few pictures in a minute, they're precast blocks. They tend to be fairly porous. So some attention would have to be made to specialty precast mixes and admixtures to reduce the porosity, to improve their freeze thaw durability. Roller compacted concrete has the same problem because of the mix proportions. It tends to be a little bit on the porous side. So for both of them, special attention would have to be made to the mix proportion. Certainly admixtures could easily be added to the ACBs. It's a little bit more difficult to get conventional admixtures to mix thoroughly in RCC because of the method that RCC uses for mixing. So usually one of the better methods when you use either RCC or ACBs is to cover it then with topsoil and seed in these extreme environments where you have extreme temperatures and a lot of freeze thaw. Now understand that if you cover it with topsoil and seed, you're essentially bringing it back to the appearance of an earth embankment, which from an aesthetic point of view is favorable compared to the exposed RCC or even the exposed ACBs. But if the dam overtops, understand that topsoil is going to be washed downstream. So there's going to be a cost to reestablish the topsoil and seed, not to mention the environmental impact of the topsoil being washed downstream. But it is fairly common to cover either one of those materials with topsoil and seed. And Karen has added that there are several ABC dams that are armored with ACBs in North Dakota. So some good questions there. So here are some photos of each of these materials. Here is roller compacted concrete being placed on the downstream slope of an embankment. This photo captures pretty much the entire process. So at the toe, you can see the staging area that's required. This is the mobile production plant. This is the plant that produces the RCC. Typically, RCC requires both a coarse and a fine aggregate, as well as cement and water. So here, this plant, this is a vertical cement silo. It does only have a limited capacity. So many times you'll see a secondary cement tanker adjacent to this. If there isn't one that's stationary, then there are cement deliveries that have to be brought into the site and this silo filled periodically with cement. Then the plant has to be fed with the aggregates. This is what this front end loader is doing back here. This is the aggregate stockpiles. In many cases, or most cases, there's both a coarse and a fine aggregate pile. So this loader is pretty much working constantly, picking up either coarse or fine aggregate from these stockpiles and delivering it into the separate hoppers that are behind this silo. And then there's a water source that, water has to be brought into this plant as well. This particular layout, the RCC is produced in this plant. There's a high velocity mixer that mixes all the different constituents together. The RCC, once it's mixed, then comes up this conveyor belt and gets dropped into these successive, these are all conveyor belts. They're obviously mobile. Here they're attached to these this wheeled piece of equipment. So this guy basically moves laterally along the base of the dam with the RCC extending up. This is a telescoping conveyor belt. So the RCC then can be dropped right on the placement surface. Again, roller compacted concrete is a zero slump, low cement content concrete. So it is basically looks and it's placed like earth fill. So this is the fresh RCC. It's so stiff. There's, like I said, no slump, so it can support a dozer on it. So a conventional bulldozer then spreads it out in front, followed by the dozer. The RCC is compacted, not by internal vibration like conventional concrete, but it's actually compacted with a vibratory roller like soil. This placement method obviously results in sort of a minimum dimension of this RCC lift of about 8 to 10 feet, because the RCC has to be placed wide enough to support the construction equipment that's placing it. So as you work yourself up, say a 2-to-1, 2 horizontal to 1 vertical downstream slope, you're placing these horizontal lifts that are, say, 10 feet wide. You end up with a normal dimension, a dimension perpendicular to the slope of RCC of about 2.5 to 3.5 foot thickness. So you're basically putting, 2 to 3 foot thick concrete on the downstream slope. That's why it's so robust and can handle pretty much any depth of overtopping. The other advantage that RCC has is because it's placed in these horizontal lifts, it results in a stepped downstream face. So when the dam does overtop, the water ends up cascading down those steps, and those steps tend to serve as energy dissipation, so that there's very little energy left in the flow at the downstream toe. So the potential for erosion at the downstream toe is minimized. And a lot of times all that's put in is like a little run out apron of RCC at the downstream toe. And I also mentioned that usually it's good practice to put a drain system in against a chimney drain in against the downstream slope prior to the RCC placement. The other material is the articulated concrete block, or ACBs. Here you can see them placed on a downstream slope. This was one of the early projects. The slope has been stripped of any topsoil. Here, a geofabric, a geotextile was put down. Now it's normal practice to put a drainage layer of crushed stone, usually like a 57 stone down, anywhere from about 4 to 6 inches. And then the articulated concrete blocks are put on top of that. You can see that these come in these mattresses, and they're tied together with stainless steel cables. The cables are looped at the ends. So when you butt one mattress up against the other, you basically leave a little gap between the two mattresses, the mattress sections, where these stainless steel cables are looped and overlapped. Then what they'll do is place a rebar through those and then place concrete or grout in that gap, so that basically you get sort of a continual support from those cables. This is an example of a small dam, relatively flat slope, as you can see, and this is a conventional reinforced cast in place concrete liner that's being put down over the downstream slope. And this is an example of a project or dam that the gabion baskets were used for overtopping protection. Similarly to the previous example, the professional services you need would be a surveyor, subsurface investigations, engineering consultant that would do the engineering design and permitting, and also an engineer. The same consultant oftentimes would provide oversight during construction. During the design or during the project in general, as the owner, don't be afraid to ask a lot of questions of your engineer during planning and design. During construction, it's typically good practice to use the same engineer for design and construction. That engineer is most familiar with the design, with the project itself, and then is in a position to address any problems or changes that come up then during construction. You want to make sure that your engineer does implement a thorough construction inspection program. You want to make sure that the construction is thoroughly inspected. The engineer should be on site during critical phases of the construction. Examples of what these critical phases might be, and this is not an all-inclusive list, but any foundation preparation, outlet work construction, whether it's spillway replacement, tower replacement, that sort of thing. Material testing, there should be an independent lab that he has on board to do material testing of, say, the concrete or placement and compaction of earth fills. He should be on site during the construction of any internal drainage or during concrete placement. Again, during construction, it's important to take a lot of photographs, either as the owner or make that a requirement of your engineer or contractor to take daily photographs of the work. It's a great way to document what's done. And then also as the owner, you would want to document any conversations you have with your engineer or your contractor. This is the summary table that I mentioned earlier, where ASDSO was tasked with coming up with what the total cost would be to rehabilitate all of the dams across the U.S. that are in need of rehabilitation. The committee that they had put together came up with sort of an algorithm or a method of doing that. And they basically broke the 90,000 some dams that are across the U.S. into 4 groups based on height. So you can see group 1 are dams up to an equal 15 feet in height. Group 2 is 16 to 22 feet. Group 3, 26 to 50. And group 4 would be dams greater than 50 feet in height. We did have there is a national database of all the dams in the U.S. And they do have height information. So we were able to get some idea of the sheer number of dams that would fill into each of those height group categories. And, the idea was to try to get roughly equal numbers, if you will, of that 90,000 dams broken up into those 4 different categories. So that's partly how we came up with those height ranges. And then through a series of sort of a flow chart of logic as far as what percentage of dams might need certain types of work, and then coming up with costs of different types of repair, we were able to actually come up with cost estimate basically per dam within those size categories. So again, this is meant to basically allow ASDSO to put a single figure on the overall need for dam rehabilitation. But from that, we were able to basically look at different size categories and say that on average, for dams that are up to 15 feet in height, that need full remediation, we're looking at perhaps something on the order of magnitude of $360,000. Then for full remediation of a dam that falls between 16 and 25, you're looking at $850, 26 to 50 foot high, you're looking at about 2.2 million, and then greater than 50 feet, you're looking at over 11 million. These numbers have just been updated for 2022, and this particular committee has also done a number of different things to try to validate these numbers, and they've recently reached out to each of the state dam safety offices and asked for data on rehabilitation projects that were performed in their state, I think in the last 5 or 10 years, and then asked for obviously rehab cost, some description of what the rehab involved, that sort of thing. And then from that data, which just recently came in, I happen to be on this committee as well, taking a look at the information. Now, we didn't get information. We only got an information, I should say, from maybe a half dozen of the states. So it wasn't terribly comprehensive as far as the number of states that we got information from, but it was, looking at it, did seem to cover a wide range of sizes of dams and rehabilitation. And then going through that data, we were able to determine that we are not too far off with these values per dam based on the actual rehab data that we're getting from actual states. So these are obviously big numbers. As a dam owner, this can be pretty pretty daunting or pretty scary when you see this. And unfortunately, the rehab of dams is a costly undertaking. As far as sources for funding, there are a number of federal programs. There was a bill recently passed, both the Senate and the House, 21st Century Dams Act. This bill reauthorized for the next, at least through 2026, the National Dam Safety Program. This was very, very important because ASDSO gets a lot of its funding through the National Dam Safety Program. It's administered through FEMA. And the FEMA also then is able to pass money down to the individual states. And I think Karen mentioned that in her introductory remarks, that it was through the money that they get from FEMA through this National Dam Safety Program that allowed them to fund this owner's education workshop, as well as a number of other things the states can do with that. So that was very important. There was a National Dam Rehabilitation Act that was signed into law back in 2016, which was a big deal at the time. It was a part or included in the Water Infrastructure Improvement to the Nations Act, which is just WIN 2016. Since then, amendments have been passed to refine that program as recently as 2020. It has yet to be funded, but in general, they're looking at providing money, grant money to states that have either grant or loan programs in place. So state dam safety program has to have some kind of funding source in place. And then they've got some kind of criteria as to how much money they would be able to funnel down to each of the states, although that hasn't actually been funded yet. NRCS, originally they were SCS, constructed tens of thousands of dams across the US under their PL 566 program. After they did the design and construction of those dams, they usually or typically turned the dams over to local watershed districts. So they have a program, small watershed rehabilitation program at the federal level, where they'll provide funding to these local watershed districts to rehabilitate these dams that were originally constructed under that PL 566 program. But the dam has to be originally an SCS dam to qualify. And then FEMA has a grant program called the Rehabilitation of High Hazard Potential Dam Grant Program. And as the name suggests, it only applies to high hazard dams. And it is a grant program and it's only, the grants would only go to states, and then the states would have to then apply them or figure out a way to get them down to the actual dam owners. But this money is not directly available to dam owners. It's only available to states, and it's only states that have enacted dam safety programs. As far as North Dakota, as far as actual state programs is concerned, they do have a cost share program where eligible dams can look for cost share through the State Water Commission. And there's a number of different types of projects and different percentages of cost share. So dams are eligible for cost share up to 60% of eligible items or costs for dam deficiencies or dam repairs, and dam breach or removal projects would fall under that. Projects to mitigate dangers associated with low head dams may receive cost share up to 75%. We talked briefly about these low head dams and how dangerous they can be for people that go float or go over these dams. They can get caught on the downstream side and drown. The development of EAPs is also eligible for cost share up to 80%. And more details on this are available at that website link that's shown in the slide. ASDSO is doing a number of things to help find funding for dam rehabilitation, because that's really the missing link here. You have owners that want to do the right thing, but maybe just aren't in a position to do it. So this is a listing of the things that ASDSO is doing. They increase appropriations. Sorry, I'm losing my voice here. Their priority legislative issues that they're focusing on are increased appropriations for that National Dam Safety Program that currently is administered through FEMA, program revisions and full appropriation for that National High Hazard Potential Dam Rehabilitation Act, increased appropriations to continue the success of the USDA Small Watershed Dam Rehabilitation Program. So those are the 3 federal programs that I had on the previous or that earlier slide. They're also making it a priority to create creation of state dam safety regulatory program in Alabama. It's the only state remaining with no dam safety legislation on the books. And they also support and appropriations for the National Levee Safety Program. Federal legislative goals that ASDSO has is to push for full funding of all federal laws that improve dam safety, to coordinate an education advocacy effort for all federal legislative initiatives, including encouraging grassroots lobbying. They encourage alternative sources of funding for dam rehabilitation and repairs through federal state partnerships and public-private partnerships, and also increase general dam safety awareness in Washington, D.C. So hopefully it stays in the forefront, the need to continue the funding of those programs. As far as the state level, ASDSO, they're increasing the network of support for states when dam safety programs are threatened. They track all legislative changes and publish summaries, provide benchmark data to states on dam safety policies. They assist state dam safety agencies with legislative awareness. They encourage policies and provide tools at the state level to increase dam safety awareness and explore funding mechanism for state dam safety programs and assist states in maintaining and increasing their budgets. Other options for dealing with these costs associated with dam rehab would be maybe to phase the repair program. So if the dam has multiple deficiencies and obviously, cash flow, ability to fund the program may not be able to fund the entire thing. You could perhaps phase it, work on the most critical elements first, and then over time address some of the other deficiencies. If possible, maybe you can transfer ownership of the dam to an entity that has more resources, more financial resources. Certainly dam removal, if the dam is no longer serving any real purpose. By removing it, obviously it removes it from the regulatory status, or decrease the size of the dam, or impoundment, which may result in a reduction in the hazard classification that would reduce maybe some of the requirements for the dam itself. So that is the end of that session, and that is the end of the workshop, at least my portion of it. Any questions on anything covered in that particular session? Okay. Jennifer, did you have some things you wanted to cover as far as the workshop evaluation and whether or not they need to take a quiz if they're looking for PDHs and that sort of thing?
Yes, I do.